Every star, every galaxy, every cloud of dust and gas is drifting, racing, or colliding in a cosmic dance that has no pause button. The ground beneath our feet feels steady, but Earth is spinning on its axis, circling the Sun at tens of thousands of miles per hour, which itself is hurtling through the Milky Way. The Milky Way is not at rest either. It is being pulled toward vast regions of unseen gravity, toward mysterious cosmic structures that span hundreds of millions of light years. From the tiniest particle to the largest supercluster of galaxies, nothing holds still. So, if everything is moving, where is it all going? What force or destination is shaping this universal flow? Before we begin, let us know where in the world you're watching from and what time it is for you right now. Like the video and drop it in the comments below. Now, settle in as we uncover what everything within the universe is actually travelling to. For thousands of years, people believed that Earth sat at the very centre of the universe. To them, it was the most natural idea in the world. They looked up at the sky every single day and saw the sun rising, crossing overhead, and setting. They saw clouds drifting calmly above, the moon glowing softly at night, and the stars scattered like shining jewels painted across a dark canvas. Everything in the heavens seemed to move, but Earth itself felt solid and unmoving. So they thought that everything, every star, every planet, every light in the night was circling around them. This belief was not limited to a single culture. It could be found in traditions from ancient China to the civilizations of the Maya in the Americas. Yet it was in the Greek-speaking world, often called the Hellenic world, that this idea grew into something more than myth. There it became not only a story people told, but also a carefully structured scientific system. And the man most responsible for turning that old belief into a detailed model of the cosmos was a scholar named Claudius Ptolemy. Ptolemy lived in Alexandria, Egypt, during the 2nd century of the Common Era, a time when Egypt was part of the Roman Empire. He was not only an astronomer, but also a mathematician and a thinker who wanted to explain the skies with precision. He inherited knowledge from Babylonian star records, Egyptian observations of the heavens, and Greek traditions of geometry. But what he did with all this information was extraordinary. He organized it, polished it, and shaped it into a grand system that he wrote down in a massive book, known later by its Latin name, the Almagest. That book was so influential that it became the main guide to the universe for more than 1,000 years. In Ptolemy's model, Earth sat still at the center of everything. Around it, in perfect layers, moved the Moon, Mercury, Venus, the Sun, Mars, Jupiter, Saturn, and finally the distant sphere of stars. Beyond that outer shell, he said, there was nothing humans could know. The universe was imagined as a series of clear crystal-like spheres, each carrying a celestial body, all rotating smoothly around the Earth. The stars were thought to be fixed to the outermost sphere, which spun once every single day, giving people night and day. This was not just a guess. Ptolemy used numbers and careful records to make his model work mathematically. He believed, like many Greek philosophers before him, that the circle was the most perfect shape. Therefore, the heavens had to move in perfect circles. But this idea quickly ran into trouble. When people tracked the planets, especially Mars, Jupiter, and Saturn, they noticed something odd. At times, a planet would slow down, stop, and even appear to move backward before continuing forward again. This strange pattern, known as retrograde motion, did not fit the idea of simple circles around Earth. To solve the puzzle, Ptolemy added what he called epicycles. An epicycle was a small circle a planet travelled along, while that small circle itself moved around Earth on a larger circle called the deferent. In other words, a planet circled a point that was itself circling Earth. This looping path could explain the backward steps people saw in the night sky. But even this was not quite enough. The numbers still did not fully match reality. So Ptolemy added another detail, the equant. This was an imaginary point slightly away from the true centre of Earth. If you looked at planetary motions from this shifted point, they seemed smoother and more regular. Ptolemy's model grew more and more detailed over the centuries. Scholars copied it, refined it, and used it. It shaped calendars, guided sailors, supported astrology, and even influenced religious beliefs. For over a millennium, this geocentric system was accepted as the truth. Yet no matter how many adjustments were made, cracks began to show. Observers grew restless. Some began to ask whether there might be a simpler explanation for the heavens. Then, in the year 1543, a quiet revolution began. A book was published that would shake the foundations of astronomy. Its Latin title was De Revolutionibus Orbium Coelestium, which means on the revolutions of the heavenly spheres. The author was not a powerful king or a famous philosopher, but a church priest named Nicholas Copernicus. That might sound unusual today, but at the time the church was the centre of learning in Europe. If you wanted to study mathematics, astronomy, medicine, or philosophy, you often did so through the church. Monasteries and cathedral schools served as libraries and laboratories of their age. Copernicus, born in what is now Poland, studied law, medicine, and even economics. He learned Greek and Latin fluently. But his true passion, the one that never left him, was the study of the sky. For many years, Copernicus observed, calculated, and quietly developed an idea that challenged everything he had been taught. He believed the sun, not the Earth, was at the centre of the universe. Earth, he argued, was a planet just like Mars or Jupiter, and it circled the sun once every single year. This was not all. Copernicus proposed that Earth itself had 3 different motions. The first was rotation. He said that Earth spins on its axis once every 24 hours. That spin explains why the stars rise and set each night. The second was revolution. He said Earth orbits the sun once per year, and that is why the planets shift their positions and why the seasons change. The third was a wobble in Earth's orientation, a slow circular tilt that we now call precession. Copernicus did not simply guess these things. He spent decades creating detailed geometric models and using trigonometry to estimate the distances of the planets from the sun. He noticed that the closer a planet was to the sun, the faster it appeared to move across the sky. That matched beautifully with his model. Still, Copernicus assumed planets moved in perfect circles just like Ptolemy. Because of that, his predictions were not much more accurate than the old system. In some cases, they were even less precise. But the real breakthrough was yet to come. Not long afterward, a new tool appeared in Europe, the telescope. It was not invented by a scientist, but by Dutch lens makers who combined pieces of glass for curious customers. News of this device spread quickly, and when it reached Italy, one man realized it could change everything. Galileo Galilei did not invent the telescope, but he transformed it into something far more powerful than a tool for sailors or soldiers. He turned it into a scientific window to the heavens. In the year 1609, he lifted his handmade telescope toward the night sky, and what he saw forever shook the foundations of the old way of thinking. The first thing Galileo studied was the moon. For thousands of years, people believed the moon was a flawless divine sphere, a perfect and polished lamp in the heavens. But when Galileo pressed his eye against the glass, he saw something that no one had truly seen before. The moon was not perfect at all. It had craters gouged into its surface, mountains that cast long shadows, and valleys that looked as rugged as the landscapes on Earth itself. The moon suddenly appeared less like a sacred jewel and more like a world. It was scarred, shaped, and rough, just like our own planet. Then Galileo turned his telescope toward Jupiter, the great giant of the solar system. There, circling around the planet, he noticed 4 tiny points of light. At first, he thought they were stars, but night after night, as he continued to watch, those little specks changed their positions. They danced around Jupiter, always staying close, never drifting far away. Galileo realized these were moons, 4 moons orbiting Jupiter. This discovery was earth-shaking, because according to the long-held geocentric model, everything in the heavens was supposed to revolve around Earth alone. Yet here was Jupiter, holding its own miniature system of worlds. Earth was no longer the centre of all motion. Galileo did not stop there. He turned his telescope toward Venus, the bright star-like planet that glows in the evening sky. What he saw became the final proof. Venus went through phases, just like the moon. Sometimes it appeared full, sometimes it appeared as a thin crescent, and sometimes it was half-lit. This could only happen if Venus was circling the sun. If Venus had orbited Earth, as the old model claimed, it would never have shown such changing shapes. The geometry simply did not work. But if Venus circled the Sun and Earth moved as well, then everything fell into place. That tiny glowing planet whispered the truth. Nicholas Copernicus had been right all along. But although Galileo revealed the vision, he was not the one who cracked the mathematics. That task fell to Johannes Kepler, a German mathematician and astronomer who was both deeply religious and fiercely precise. Kepler's life changed when he became the assistant to Tycho Brahe, the last great astronomer who had studied the skies without a telescope. Tycho Brahe was a Danish nobleman with an obsession for accuracy. For decades, he built enormous measuring instruments on his private island observatory. Without a telescope, he charted the positions of planets with extraordinary precision, carefully writing down their movements night after night. Yet Tycho did not fully accept the Copernican model. Instead, he created his own hybrid theory. He believed that the planets circled the Sun, but that the Sun itself circled Earth. It was an attempt to compromise between tradition and new ideas. When Tycho died in the year 1601, his treasure trove of planetary data passed into Kepler's hands. Kepler threw himself into the work, determined to see if the Copernican system could truly match Tycho's careful records. He focused especially on Mars, but Mars was a troublemaker. It did not move smoothly across the sky. Sometimes it raced ahead, sometimes it slowed down, sometimes it looped backwards in strange retrograde paths. For years, Kepler tried to force Mars into neat circular orbits, because circles were thought to be divine and perfect. But no matter how hard he tried, the math refused to fit. At last, Kepler surrendered his preconceptions. He allowed the data to speak for itself, and when he did, the heavens revealed their secret. Mars, and indeed all the planets, did not move in perfect circles at all. They moved in stretched ovals, ellipses. This became Kepler's first law of planetary motion. All planets travel in elliptical orbits with the Sun resting at one focus of the ellipse. But Kepler did not stop there. He noticed another pattern. As planets journeyed around the Sun, they did not travel at the same speed. They swept faster when they were closer to the Sun and slowed down when they drifted farther away. This became Kepler's second law. A line drawn between a planet and the Sun sweeps out equal areas in equal times. No matter how far or near a planet is, the area it covers in a given stretch of time is always the same. This explained the erratic behaviour of Mars and gave harmony to the heavens. Finally, Kepler uncovered the third law, the law of periods. He discovered that the time a planet takes to orbit the Sun is related to its distance from the Sun. In simpler words, the farther a planet lies from the Sun, the longer its year will be. The relationship was mathematical and precise, a universal rhythm of cosmic motion. With Galileo's telescope and Kepler's mathematics, humanity was given both vision and proof. Copernicus had lit the spark. Galileo fed it with fire. Kepler built the framework of laws that allowed the fire to endure. And yet, after these discoveries, one great question remained. Why did the planets move at all? What force kept them circling instead of flying off into space or crashing into the Sun? The answer came with Isaac Newton and the story of the falling apple. Newton gave the invisible force a name, gravity. He realized that the same pull that dragged an apple to the ground also held the moon in its orbit, kept Earth tethered to the Sun, and controlled the grand dance of the planets. He formulated the law of universal gravitation. Every object with mass pulls on every other object, and the strength of the pull depends on how massive the objects are and how far apart they lie. With this law, Newton unified heaven and earth. The same rules that guided an apple's fall also governed the motion of the stars. Using Newton's equations, astronomers could now calculate how fast Earth moves around the Sun. About 107,000 kilometers every hour, which is nearly 30 kilometers every second. Mercury, being closer to the Sun, races even faster, about 47 kilometers every second, while Mars, farther out, moves more slowly. The pattern made sense. The closer a planet is to the Sun, the faster it must move to remain in orbit. Newton's work stitched the final thread into the fabric of cosmic understanding. For the first time in history, humanity possessed one set of laws that applied everywhere, from the falling of stones to the spinning of galaxies. Yet even then, a deeper mystery stirred. As astronomers sharpened their instruments and refined their calculations, they realized something astonishing. The sun itself, which for centuries had seemed to be the unmoving anchor of the heavens, was not still at all. It too was moving, carried along in an even greater cosmic journey. The sun itself, which for centuries had seemed to be the unmoving anchor of the heavens, was not still at all. It too was moving, carried along in an even greater cosmic journey. After the great Copernican revolution, the world changed forever. The Earth was no longer seen as the fixed centre of creation. Instead, the sun took its place at the centre, while the Earth was understood to spin on its axis and to circle around the sun. This shift was more than a new idea. It was a complete overturning of how people had viewed the cosmos for thousands of years. At first, it felt shocking and even dangerous to many. But as the new model, the heliocentric one, became accepted, it settled into people's minds. The sun, once thought to be just another glowing light in the heavens, was transformed into something far greater. It became the solid anchor of everything, steady and unmoving, the great lamp at the centre of the universe, and for a few centuries this picture remained unchallenged. But that would not last. The challenge would not come from a philosopher or a physicist, but from a man whose first passion was music. William Herschel was born in Germany in the year 1738. As a young man, he moved to England, not as a scientist, but as a composer of music. Yet alongside his career, he developed an obsession: telescopes. In his spare hours, he taught himself how to grind mirrors and polish lenses. His designs were so advanced that they rivaled and often surpassed the best instruments of his time. When Herschel lifted these telescopes to the night sky, he did not just gaze. He measured, he counted, and he sought patterns. He wanted to know if the countless stars above were scattered at random, or if they formed an order, a structure. With the help of his sister, Caroline Herschel, he began a colossal project, surveying the heavens. Night after night, he counted the stars in thin strips of the sky, carefully recording how many appeared in each direction. Slowly, these numbers began to form a picture. Herschel noticed that in some parts of the sky there were many more stars, especially along a faint glowing band, the Milky Way. From this, he created a map. The stars, he realized, were not endless in every direction, but instead formed a vast flattened system, like a great wheel or disk. And at the center of this imagined system, Herschel placed the sun. Today, we know that he miscalculated the size. He could not have known that clouds of interstellar dust were hiding many of the farthest stars from view, making the universe look smaller than it truly was. But for the late 18th century, his insight was extraordinary. He had shown that the stars were not infinite, but belonged to a grand structure, a system we were part of. He named it the Galactic system. Herschel did not realize that the hazy patches of light he sometimes saw, the so-called nebulae, were in fact whole galaxies of their own, unimaginably far away. But even without that knowledge, his work was revolutionary. He had proved that humanity was not at the center of everything, not even close. His flat star map carried a hidden message. If the Milky Way had a shape, then it also implied that it had direction and motion. If the stars formed a system with a structure, then the sun, and the Earth with it, had a location. And if it had a location, perhaps it was also moving. That question, are we in motion, and how can we tell, began to trouble astronomers. But there was a deeper difficulty. Every observation we make of the cosmos is from Earth. Our eyes, our telescopes, our instruments, all of them rest on this restless planet, which itself spins on its axis and orbits the sun. And perhaps the sun itself might be moving too. How then can anyone decide what is truly still and what is moving? This is where the idea of a frame of reference becomes important. Consider a simple thought experiment. You are sitting inside a train. The carriage feels calm. A cup of coffee sits steady in your hand, a book rests quietly on your lap. Through the window, you see another train beside yours. For a moment, it looks as though that train is sliding backward. But then you wonder, are you the one moving, or is it the other train, or are both in motion? Without seeing the ground, you cannot be certain. From inside your train, the world feels still. Yet to someone standing on the platform, you're rushing by at 80 kilometers an hour. Both views are correct because motion is not absolute. It is always relative. And so it is with the universe. From our moving Earth, circling a moving sun, it becomes a puzzle to decide what is truly in motion. One man quietly took on this puzzle, Jacobus Kapteyn. He was not a loud revolutionary, but a patient, careful thinker who loved numbers more than drama. Born in the Netherlands in the mid-19th century, he lived at a time when Herschel's maps were already more than a century old. By then, most scientists agreed that the Sun was inside a star system, the Milky Way. But the true shape and motion of that system remained a mystery. Kapteyn began his work not with grand theories, but with patient collection of data. He studied not only the brightness and position of stars, but also their proper motion, the tiny shifts in their positions over years and decades. These movements were incredibly small, often no more than a fraction of an arc-second each year, but with careful mathematics they told a story. To build this story, Kapteyn gathered star observations from all over the world, from observatories in South Africa, in Argentina, in Australia, and beyond. Piece by piece, he compiled enormous catalogues containing the measured positions, motions and brightness of thousands of stars. And then a remarkable pattern emerged. The stars were not drifting randomly. They seemed to form two great streams, moving across the heavens like cosmic currents. At first, this looked as though the stars were arranged in two huge swarms, each rotating in its own direction. But Kapteyn thought differently. He realized that the effect might not be caused by the stars themselves, but by our own motion. Like a person walking through a crowded plaza, the people around you seem to flow past in different directions, but in truth, it is you who are moving. Kapteyn applied his calculations and everything fit. The pattern of stellar motion only made sense if the Sun itself was drifting through space, carrying the Earth and all its planets with it. This direction of travel became known as the solar apex. According to Kapteyn's results, the Sun was moving steadily toward a point in the constellation Hercules at about 20 kilometers per second. Not a fiery sprint, but a calm, relentless glide through the galaxy. With that discovery, the Sun lost its imagined stillness. Yet Kapteyn wanted to go further. If we are in motion, then what is the greater system we are moving inside? What is the shape of the Milky Way? Using his data on stellar motions and brightness, Kapteyn constructed what he believed to be the true form of our star system. Assuming that stars were evenly distributed in space and that they grew fainter with distance, he built a model of a great flattened disk, about 40,000 light-years across. In this structure, Kapteyn placed the Sun close to the centre. It was humanity's first real attempt to map the Milky Way as a whole. Today, we know his model was too small, because he did not yet know about the dark clouds of interstellar dust that block the light of distant stars. This made the galaxy look smaller and simpler than it really was. But for his time, Kapteyn's work was astonishing. He had taken the scattered motions of the stars and turned them into a cosmic map. Then came a true turning point in the history of astronomy. For centuries, people had stared at the night sky and noticed faint misty patches scattered among the stars. These were called the spiral nebulae. At first, most astronomers thought they were simply gas clouds or small clusters of stars inside our own Milky Way galaxy. But some began to wonder if they were actually something far larger, perhaps entire star systems of their own, islands of stars far beyond the borders of our galaxy. This debate set the stage for one of the greatest discoveries in science, and it was Edwin Hubble who changed everything. At the time, Hubble worked with a Hooker telescope on Mount Wilson in California. This telescope, the most powerful in the world in the early 20th century, had a mirror over 2.5 meters across, making it capable of seeing deeper into the cosmos than any instrument before it. In the year 1923, Hubble turned this giant eye of glass and steel toward the Andromeda Nebula, one of the brightest of those mysterious patches in the sky. What he found inside would forever change our view of the universe. Hidden among Andromeda's countless stars, Hubble spotted a special type of star called a Cepheid variable. These stars are not steady in brightness. Instead, they pulse. They grow brighter and dimmer in a repeating pattern. The length of this cycle is tied directly to the star's true brightness. Years earlier, Henrietta Swan Leavitt, a brilliant astronomer at the Harvard College Observatory, had worked out the exact relationship between a Cepheid's pulsation period and its luminosity. That discovery meant that astronomers could now use Cepheids as cosmic yardsticks. By measuring how bright they appeared from Earth and comparing it with their true brightness, one could calculate their distance. Hubble made the calculation, and the result shocked him. The Cepheid in Andromeda was so faint that it had to be unimaginably far away, millions of light-years distant. It was far beyond the edge of the Milky Way. That meant Andromeda was not a small cloud inside our galaxy. It was a galaxy of its own, an entire star system containing billions of stars. This discovery was a revolution. For all of human history, people had believed that the Milky Way was the entire universe. Now it was only one galaxy among many, a single island adrift in a vast cosmic ocean. And this revelation brought something else: perspective. We live inside the Milky Way. Because of this, we cannot step outside it to view its shape. It is like standing at the base of a single tree and trying to describe the form of an entire forest. But by studying other galaxies, astronomers suddenly had mirrors to compare against. They could ask questions. Does our galaxy have spiral arms like Andromeda? Does it have a central bulge of stars, a halo surrounding it, a flat rotating disk? By comparing the Milky Way with these other cosmic systems, they began to piece together its structure. Over the decades that followed, astronomers made steady progress. They mapped the distribution of gas clouds, clusters of stars, and different populations of stellar groups. They invented new methods of observation, like radio astronomy, which could cut through the thick curtains of interstellar dust that block visible light. Slowly, a more detailed picture of the Milky Way took shape. Among those working on the mystery was a Dutch astronomer named Jan Oort. He studied the motions of stars in our part of the galaxy, near the Sun. He noticed something curious. The stars did not move as they would if the Milky Way were a solid wheel. In a wheel, like the spokes of a bicycle, every part turns at the same angular speed. But the stars did not behave this way. Some lagged behind, others raced ahead. The galaxy, Oort realized, rotated more like a whirlpool, with the inner parts moving faster than the outer regions. By working out the mathematics, Oort discovered two constants, now called the Oort constants, that described the motion of stars near the Sun. Using these, he estimated that our Sun sits about 30,000 light-years from the centre of the Milky Way. He also calculated that the Sun is racing around the galactic centre at more than 200 kilometers per second. To put that speed in perspective, it is fast enough to circle the entire Earth 7 times in a single minute. At that breakneck pace, the Sun takes about 225 million years to complete one orbit of the galaxy. Astronomers call this enormous time span a galactic year, and every star you see at night is taking part in the same journey, orbiting the invisible centre of our galaxy like bees swarming around a hive. But what exactly was at the centre, powerful enough to hold all this together? To answer this, astronomers needed instruments that could see what ordinary telescopes could not. They turned to radio astronomy once again, focusing on the natural 21-centimetre radio signal emitted by neutral hydrogen atoms. This faint signal passes through dust clouds that block visible light, making it perfect for mapping the Milky Way's spiral arms from the inside. Then came another leap forward, the Very Long Baseline Array, or VLBA. Unlike a single telescope, the VLBA is a network of 10 giant radio antennas spread across thousands of kilometers, from Hawaii to the Virgin Islands. By linking them together with exquisite precision, astronomers created a virtual telescope as large as a continent. With this, they could detect motions in the sky so tiny they were measured in millionths of a degree, small enough to spot a coin lying on the surface of the Moon from Earth. They used the VLBA to track cosmic beacons known as masers, powerful bursts of radio light emitted by clouds of gas around newborn stars. Masers are bright, compact, and anchored to specific regions in the galaxy, making them excellent reference points. By following these masers year after year, astronomers could measure their positions and movements with astonishing accuracy. They combined proper motion, the slow drift across the sky, with radial velocity, the shift in wavelength showing whether the object was moving toward or away from us. Together, these gave a full 3-dimensional map of stellar motion. This revealed the great dance of the Milky Way. Stars circled the centre, not in perfect circles, but in winding spiral patterns twisted by gravity. Some arms led ahead, others trailed behind. Gas clouds stretched and sheared under tidal forces, Star clusters wobbled along their orbits, and at the very heart of this dance lay something truly strange. Objects near the galactic centre were whipping around at ferocious speeds, far faster than visible matter alone could explain. There simply was not enough mass, stars, gas, dust, to create the required gravity. Something invisible was holding the galaxy together. All the calculations pointed to a small, dense, radio-bright spot near the constellation Sagittarius. This mysterious region became known as Sagittarius A. Radio observations focused in, and the evidence grew undeniable. At the centre was an object with a mass more than 4 million times that of our Sun, yet packed into a space smaller than the orbit of Mercury. No known object in physics could match such density and mass, except a black hole. Sagittarius A is now known as a supermassive black hole, the anchor of the Milky Way. It sits there quietly, mostly hidden, while stars, planets, and gas clouds swirl endlessly around it. Yet even this is not the end of the story. Our galaxy is not frozen in space. It twists, warps, and wobbles as it rotates. The arm of the galaxy where we live, called the Orion Spur, rises and falls gently above the galactic plane, as if riding a wave, and beyond that, the Milky Way itself drifts through the universe, pulled by unseen forces, part of an even larger cosmic dance stretching across intergalactic space. If a star or an entire galaxy is moving toward us, its light waves get squeezed, and the light shifts ever so slightly toward the blue side of the spectrum. We call this blue shift. If the star or galaxy is moving away, the light waves stretch out instead, shifting toward the red side. That is what scientists call the red shift. In the years of the 1910s and 1920s, astronomers began using this clever trick to measure the movements of stars and galaxies. Among them was a man who would forever change our view of the universe, Edwin Hubble. His discoveries were nothing short of astonishing. When Hubble looked at distant galaxies, he found that most of them were not sitting quietly in space. Instead, they were racing away from us. Even more surprising, the farther away a galaxy was, the faster it was speeding off. Some were fleeing at hundreds of kilometers per second, while others were rushing away at thousands. Every new observation confirmed the pattern. The farther, the faster. This could only mean one thing. Space itself was expanding, and galaxies were simply carried along for the ride. It was one of the greatest breakthroughs in the history of science. It told us that the universe had a beginning, that everything we see today was once packed much closer together. It even set the stage for what would later be called the Big Bang Theory. But not every galaxy is running away. One in particular stood out, a massive spiral-shaped neighbour that we know as the Andromeda Galaxy. In the year 1912, an American astronomer named Vesto Melvin Slipher pointed his telescope toward Andromeda and studied its spectrum of light. At that time, the idea of redshift and blueshift in galaxies was still very new. What Slipher discovered shocked everyone. Andromeda's light was not redshifted, like almost every other galaxy. It was blueshifted. That meant it was not fleeing from us. It was heading straight in our direction. Back then, astronomers could only say that Andromeda was moving toward us. They did not have the tools to figure out the complete picture. But fast forward one full century, and the story becomes clearer. Today, we have powerful space telescopes, giant supercomputers, and networks of radio dishes spread across the Earth. Astronomers combine data from NASA's Hubble Space Telescope, the highly precise Gaia mission, and the very long baseline array of radio antennas. By carefully tracking Andromeda's motion over many years, they created a full three-dimensional map of its path. The result was clear. Andromeda is not just drifting nearby, nor is it going to swing past us harmlessly. It is locked onto a direct collision course with our own Milky Way galaxy, and we are rushing toward it too. At this very moment, Andromeda is barreling toward us at about 110 kilometers per second. That equals more than 400,000 kilometers every single hour. But the Milky Way is not sitting still either. Our entire galaxy, when you include the motion of our local group of galaxies, is drifting toward Andromeda at nearly 300 kilometers per second. Added together, that means the gap between us is closing at a staggering speed of about 500 kilometers per second. Yet space is unbelievably vast. Andromeda is roughly 2.5 million light-years away. That distance equals about 24 quintillion kilometers, a number so unimaginably large that it almost loses meaning. So even though the two galaxies are rushing toward each other at incredible speeds, the meeting will not happen tomorrow, nor next year, nor even in the next million years. The actual collision will occur in about 4 to 5 billion years. Now, it might be tempting to picture this galactic meeting as a fiery crash. Stars smashing into stars, chaos, destruction, and explosions everywhere. But that is not how it will play out. Galaxies, despite their bright appearance, are mostly empty space. The stars inside them are incredibly far apart from one another. Here in our corner of the Milky Way, the average distance between two stars is about 4 to 5 light years. That equals nearly 40 trillion kilometers. Even in the densest regions, stars are usually separated by at least a full light year. To put that into perspective, if one star were the size of a ping-pong ball, the nearest star would be several hundred kilometers away. This means that when the Milky Way and Andromeda finally collide, most stars will simply drift past one another, untouched, like ships gliding silently in the night. Still, it will not be completely calm. In the crowded central regions, some stars might actually collide. Others, especially those at the outer edges, could be flung completely out of their galaxies, hurled into the dark wilderness of intergalactic space. But the real fireworks will not come from stars smashing together. They will come from gravity. This invisible force will stretch, twist, and reshape both galaxies. Long, thin tidal tails of stars will be pulled out like streamers. Spiral arms will be ripped apart. The dense cores will be dragged closer and closer until the two galaxies finally merge into one enormous, messy system. The full merger will not happen instantly. The first encounter will be a fast, close pass that begins the chaos. But the true merger, the slow, gravitational dance, will take about 1 to 2 billion years to settle. It will not be a violent crash. It will be more like a long, graceful cosmic ballet. And when the performance is over, something new will be born. The Milky Way and Andromeda will merge into a single giant elliptical galaxy. Astronomers have even given it a name, Milkomeda. It will not have the elegant spiral arms we see today. Instead, it will become puffier, rounder and brighter, a glowing ball of stars, gas and dust. Our Sun, if it still survives, will likely end up in a new orbit, far different from the one it has today. It may drift farther from the centre, following a more erratic path through this reshaped galaxy. Yet this story of Andromeda and the Milky Way is not the end. It is only one chapter in the much larger journey our galaxy is taking. Together with Andromeda and hundreds of other galaxies nearby, we are all being pulled towards something even greater and stranger. To understand where we are truly headed, we must zoom out far beyond the solar system, past the Milky Way itself, and even beyond our local group of galaxies. For galaxies are not scattered at random. They gather in clusters, drawn together by gravity, flowing across the cosmic landscape the way water finds its path downhill. Our Milky Way is not alone in space. It belongs to a family of galaxies known as the Local Group. This group contains roughly 80 galaxies, both large and small, spread out across a region about 10 million light-years wide. Within this family, the two giants stand out, our own Milky Way and the mighty Andromeda galaxy. Each of these big galaxies is surrounded by smaller companions called satellite galaxies that orbit them like moons around a planet. For the Milky Way, these include the large and small Magellanic Clouds. For Andromeda, tiny galaxies like Messier 32 and Messier 110 whirl around it like loyal followers. But the Local Group is just one small neighbourhood in the much larger cosmic city. Step one level higher and you reach galaxy clusters. These are massive gatherings of galaxies where several galaxy groups are bound together by gravity. Our Local Group is a mere member of the Virgo cluster, a vast congregation of more than 1,000 galaxies. The Virgo cluster lies about 65 million light-years away, and its gravitational pull tugs on us constantly. We are not drifting aimlessly near it. The entire Local Group, including the Milky Way, is hurtling toward the Virgo cluster's centre at a breathtaking speed of roughly 600 kilometers per second. Yet even clusters are not the final word in cosmic organisation. Clusters themselves can gather into even larger structures called superclusters, the grandest formations in the observable universe. These cosmic giants can stretch across hundreds of millions of light-years and cradle tens of thousands of galaxies. Our home supercluster is named Laniakea, a Hawaiian word meaning immense heaven. The name fits perfectly, for Laniakea is truly vast, spanning more than 500 million light-years and housing nearly 100,000 galaxies. Within it lie famous clusters such as Virgo, Hydra Centaurus, Pervo Indus, and the Southern Supercluster, all connected by a delicate cosmic web of galaxy flows. How, then, do scientists know all this? How can they tell where galaxies are, how fast they move, and what direction they are heading toward? The answer lies in studying motion. Over the past several decades, astronomers have not only mapped where galaxies sit in the sky, but also traced their movements. To do this, they needed more than the familiar red shifts and blue shifts that reveal galaxies moving away or toward us. They had to measure something trickier, peculiar velocity, which is the motion of galaxies compared to the general expansion of the universe itself. Measuring this sideways drift through space is not simple. You cannot just take a picture and know. Astronomers rely on clever tools, one of the most important being the Tully-Fisher relation. This method links the brightness of a spiral galaxy with how fast it rotates. By comparing how bright a galaxy should be to how bright it actually looks from Earth, astronomers can estimate its distance. And if they know both the distance and the redshift, they can tell whether the galaxy is moving faster or slower than the universe's general expansion. That difference reveals its peculiar velocity, motion caused by local gravitational influences rather than cosmic expansion alone. These measurements became the foundation for the Cosmic Flows surveys. Cosmic Flows 2 and later, the even more detailed Cosmic Flows 3, gathered enormous amounts of data, charting the movements and distances of thousands of galaxies. They used methods such as the Tully-Fisher relation, surface brightness fluctuations, and even type Ia supernovae as cosmic yardsticks. With this information, scientists built a three-dimensional velocity map of our cosmic neighborhood, not just where galaxies are, but how they are flowing through space. And the results were astonishing. The galaxies were not simply scattering outward like dots on an inflating balloon. Instead, they were streaming in a coherent direction, flowing toward a mysterious region hidden behind the thick dust lanes of our Milky Way, somewhere beyond the constellations Centaurus and Norma. This unseen source of gravitational pull became known as the Great Attractor. The Great Attractor was first suspected in the 1970s when astronomers noticed that galaxies, including our own, were sliding sideways across space at hundreds of kilometers per second, as though pulled by something massive. Yet when telescopes turned in that direction, they hit the so-called zone of avoidance, a crowded stretch of sky blocked by the Milky Way's own stars, dust and gas. Still, the motion could not be denied. The gravitational grip was real, even if the object itself could not be seen directly. Over time, with the help of X-ray observatories and infrared surveys that could peer through the dust, astronomers pieced together the puzzle. They discovered vast masses of galaxies clustered in that hidden region. One of the biggest was the Norma cluster, lying about 220 million light-years away. But Norma was not alone. It was part of something far greater, the Shapley supercluster, one of the largest known superclusters in our local universe. The gravitational might of the Shapley supercluster bends the paths of galaxies over enormous stretches of space, and it is this colossal structure that is dragging our local group, our Virgo cluster, and indeed the whole Laniakea supercluster in its direction. Yet our journey is not a straightforward fall into this cosmic giant. Space is not a simple playing field, and gravity does not act like a rope pulling in a single direction. Instead, we are caught in a cosmic tug-of-war. While the Great Attractor and Shapley supercluster pull us one way, another influence shapes our course in an entirely different manner, the mysterious dipole repeller. The dipole repeller is not an object. It is not a cluster or even a galaxy. It is a cosmic void, a vast empty region of space almost completely devoid of matter. And emptiness, strangely enough, has power. While massive structures pull galaxies toward them, immense voids act like open gates, allowing galaxies to drift away more freely. Imagine yourself floating in a river. On one side, a roaring waterfall tugs you forward. That is the Great Attractor. On the other side, the water is calm and flat. That is the dipole repeller. You're not being pushed by it, but you're not being held back either. Naturally, the pull of the waterfall wins, and you drift toward it. In the year 2017, using data from Cosmic Flows 3 that mapped the motions of over 18,000 galaxies, astronomers finally confirmed this picture. They saw not only a pull toward the Great Attractor, but also a flow away from the dipole repeller, a dipole pattern shaping the movement of galaxies across the nearby universe. And when you zoom out farther still, beyond galaxies, clusters, superclusters, beyond the filaments and voids, an even deeper motion becomes visible. The great threads of the cosmic web themselves are not fixed. They too are drifting, sliding, and flowing across the vast expanse of the observable universe, all moving towards some grander, still hidden destination. As the universe keeps on stretching and growing, something truly breathtaking is taking place. The galaxies that are far away from us are drifting even farther, and they are doing so at faster and faster speeds. It is not because they are racing through space like rockets. The truth is far more wondrous. The very fabric of space itself is stretching, and as it stretches, it carries those galaxies along with it, as if they are passengers on an invisible current. This great stretching of space is not slowing down. Quite the opposite. It is speeding up. Scientists call this the accelerating expansion of the universe. What this means is that with every passing moment, galaxies are moving away from us more and more quickly. The farther a galaxy is from us, the faster it seems to flee into the distance. And one day, some galaxies will be moving away so swiftly that, from our point of view, they will appear to be travelling faster than the speed of light. At first, this sounds like it breaks the rules of nature, because we often hear that nothing can move faster than light. But here is the twist. Those galaxies are not actually breaking any cosmic speed limits. They are not moving through space that quickly. Instead, it is the space between us and them that is growing. This stretching of space is perfectly allowed by the laws of physics. You can think of it like raisins in bread dough. The raisins are not racing around inside the dough, but as the dough rises and swells, the raisins are pushed farther and farther apart. This detail is very important, because it tells us something astonishing about the future of the universe, a future that is both fascinating and a little lonely. As space continues to expand, the most distant galaxies will drift so far away that even their light will never reach Earth again. They will vanish from our sight, not because they are gone, but because their light can no longer keep pace with the swelling fabric of space. At that point, they will cross what scientists call the cosmic horizon, the ultimate boundary of what we can ever hope to see. This is not some far-off dream. It is already happening. Right now, there are galaxies so unimaginably far away that the light we see from them today began its journey billions of years ago. And as the years roll by, that light will be stretched more and more by the expanding space. This stretching of light is called redshift, because it pushes the light toward the red end of the colour spectrum. The faster a galaxy recedes, the more stretched and redshifted its light becomes. Eventually, the light from these galaxies will be stretched so much that it will slip beyond what our eyes and even the most powerful telescopes can detect. First, it will slide into the range of microwaves, then into radio waves, and at last it will fade completely beyond detection, lost in the darkness. If we leap forward billions of years into the future, most of the galaxies in the universe will have already disappeared beyond our cosmic horizon. The only ones that will still remain visible to us will be those that are tied to us by gravity, our small cosmic family. These galaxies make up what astronomers call the local group, which includes our Milky Way, the mighty Andromeda galaxy, and a sprinkling of smaller galaxies nearby. Because gravity holds them together, these galaxies will not drift apart. Instead, over time, they will slowly draw closer and eventually merge into a single enormous galaxy. Beyond this small family, however, the rest of the universe, with all its galaxies, stars and wonders, will slip quietly out of view, one by one, into the endless dark. This paints a picture of a universe that becomes lonelier as the ages pass. Each distant galaxy that disappears takes with it its light, its history, and its part in the grand cosmic story. Future astronomers, living trillions of years from now, may look up at the night sky and see only one massive galaxy, the final union of the Milky Way and its neighbours. They might never realise that once upon a time, a vast universe filled with countless galaxies lay beyond their view. In the early days of the universe, galaxies often collided and merged, sparking bursts of starbirth and dramatic changes. But as the centuries and millennia stretch into billions of years, and the galaxies drift farther apart, such fiery encounters will become rare. The universe will grow quieter, calmer, and far more solitary. And in the far, far future, long after the last galaxy has slipped beyond our sight, the universe will change even more. The stars in our galaxy will keep shining for billions of years, but eventually even they will run out of fuel. No new stars will be born. One by one, the stars will fade, and the universe will grow colder and darker. This final chapter is called the heat death of the universe, a time when all energy is used up, when stars and galaxies no longer burn, and when the cosmos itself falls into deep stillness. So far, the expansion of the universe has not rewritten the laws of physics, but it has stretched the way those laws play out on the grandest scales. The basic rules, gravity, thermodynamics, quantum mechanics, still hold firm. Yet the conditions under which they act are shifting, shaping the destiny of everything we see. Still, some scientists wonder, could this endless stretching of space eventually change the very laws of nature themselves? It is a daring and thought-provoking question, one that challenges the old belief that the constants of physics, like the speed of light, the strength of gravity, or the fine structure constant that shapes how light interacts with matter, are fixed and eternal. What if they are not? These constants are like the foundation stones of reality. The speed of light, for example, is not just about how quickly light travels. It sets the ultimate speed limit for all information in the universe. The gravitational constant dictates how strongly objects pull on each other, from the Earth holding the Moon, to the Sun binding the planets, to galaxies themselves staying together. Without it, there would be no stars, no worlds, no galaxies. For now, all evidence shows that these constants do not change. The universe is expanding, yes, but it is still playing by the same rules. Yet the more we look to the far future, the more we wonder, is the foundation of reality truly unshakable? Or is there still some hidden twist waiting to be revealed in the great cosmic story? Another important player in the story of the universe is something called the fine structure constant. This is a number that decides how light and tiny charge particles, like electrons and protons, interact with each other. It is a major factor in chemistry, in the way atoms hold together, and in how matter forms and behaves. Even the smallest change in this number could completely transform the universe. Imagine a universe where atoms could not exist, where stars might never light up, and where life as we know it could be impossible. Now, here is where the story becomes even more fascinating. As the universe expands, driven by the mysterious force we call dark energy, space itself is stretching, almost like a balloon that keeps inflating. This cosmic stretching pushes galaxies farther apart and shapes the universe on a grand, unimaginable scale. But could this stretching of space also affect the fundamental rules that govern everything within it? Some scientists believe this might be possible. They propose that the constants we measure today, like gravity or the strength of the electromagnetic force, may not have always been exactly the same. Perhaps billions of years ago, the universe operated under slightly different rules. If that were true, the early universe could have been very different, shaping the way the first stars and galaxies were born. One constant that has especially captured the attention of researchers is the fine structure constant. A few studies have suggested that this number might have been just a tiny bit different billions of years ago. This idea is still debated and far from proven, but if it turns out to be correct, it could mean that the universe's expansion, or perhaps other unknown cosmic forces, can slowly influence the very laws of physics. And then there is dark energy. We still do not fully understand what it is or how it behaves. Some theories suggest that dark energy could be connected to the universe's evolving nature, and that it might even have the power to subtly influence the fundamental constants of physics. But the mysteries do not end there. Some scientists have speculated that the ongoing expansion of space might even alter our experience of time itself. As space stretches, light waves grow longer and distances between objects increase. Could time itself be stretching along with space? Could the very flow of time be changing in a deep and fundamental way? Even stranger ideas have been suggested. Some researchers imagine that as the universe continues to expand and cool over unimaginable eons, it might eventually undergo massive transformations, known as phase transitions. Similar to how water turns into ice when it becomes cold enough, the universe itself might shift into a completely new state. In this future state, the laws of physics could rearrange themselves. New rules might emerge and old ones could disappear. This could happen trillions of years from now, leaving a universe that is utterly unfamiliar, something beyond anything we can picture today. At the very beginning of the 20th century, most scientists believed that the universe was calm, permanent, and unchanging. The common belief was that the cosmos had always existed exactly as it looked, with stars shining in their places and galaxies fixed forever, like jewels pinned on a velvet cloth. People thought the universe was eternal, still, and unshakable, a grand stage that had never moved and never would. But this old idea did not last. A new generation of astronomers began to study the heavens with sharper eyes, carefully examining the light that streamed from faraway galaxies. Among them was one man whose work would forever transform our understanding of the cosmos. His name was Edwin Hubble, an American astronomer who stood at the frontier of discovery and changed the story of the universe. Hubble worked at the famous Mount Wilson Observatory in California. There, he had the privilege of using a powerful new machine, the Hooker telescope. This telescope had a mirror 2.5 meters wide, which in those days made it the most powerful telescope in the entire world. With it, Hubble could peer deeper into the night sky than anyone had ever done before. He could study faint ghost-like smudges of light that earlier astronomers had seen but never truly understood. For a long time, scientists argued about these fuzzy patches. Were they simply clusters of stars inside our own Milky Way galaxy? Or were they something much bigger and far more mysterious? Using the Hooker telescope, Hubble made a discovery that shook science. Many of those faint smudges were not inside our galaxy at all. They were entire galaxies of their own, each holding billions of stars scattered far beyond the Milky Way. With this single discovery, the universe suddenly grew much larger in human imagination than anyone had ever dreamed. But Hubble's journey did not stop there. As he looked more closely at the light from these distant galaxies, he noticed something strange. When astronomers study starlight, they break it down into its spectrum, a rainbow of colours that reveals the secrets of the stars. Hubble saw that the light from many galaxies was shifted toward the red side of the spectrum. This effect was called redshift. Redshift is what happens when light waves are stretched out, making them look redder than normal. A good way to imagine this is by thinking about sound. When an ambulance races past you, its siren sounds high-pitched as it comes closer, but lower and stretched out as it drives away. That effect with sound is called the Doppler effect. Redshift is the same idea, but with light instead of sound. This discovery carried a stunning message. The galaxies Hubble studied were not standing still. They were moving away from us. Even more surprising, the farther away a galaxy was, the faster it seemed to be racing away. This was not just a random occurrence in a few places, it was a consistent pattern across the universe. This great discovery became known as Hubble's law. What did all this mean? It meant that the universe itself was expanding. The galaxies were not simply drifting through space like ships on an ocean. Instead, space itself was stretching, carrying galaxies farther apart as if the cosmos were a giant balloon being slowly inflated. And if the universe is stretching apart now, then long ago it must have been smaller and smaller. If we trace that expansion backward through time, it suggests there was once a moment when everything, all matter, all energy, the very fabric of space itself, was crammed together in one incredibly tiny, hot and dense point. Then, in a dramatic instant, it began to expand outward. This powerful idea became known as the Big Bang theory, the theory that the universe had a beginning, not eternal and unchanging, but dynamic, alive, and still unfolding. When people hear that the universe is expanding, many imagine a dramatic picture. Galaxies and stars blasting away from each other like rockets, zooming in every direction across a vast emptiness. But that is not really what is going on. The truth is even stranger and more wonderful. The galaxies themselves are not racing through space the way cars speed down a highway. Instead, the very space between them is stretching and growing, and the galaxies are being carried along with it like passengers riding on a moving walkway. This small but important difference changes everything about how we imagine the universe. When scientists say the universe is expanding, they do not mean galaxies are simply drifting apart like boats on a lake. They mean that the invisible fabric of space itself is swelling larger and larger with time, and galaxies are caught up in that stretching. One of the best ways to picture this is with a balloon. Imagine drawing tiny dots on the surface of a balloon. Each dot stands for a galaxy. As you blow air into the balloon, the surface stretches, and the dots move farther away from one another. The dots are not crawling over the balloon's surface, they are fixed in place. It is the balloon itself that grows. This is almost exactly how the real universe works. This idea that space is expanding instead of objects just moving through it is not just a fun thought exercise. It changes how we see the entire cosmos. Normally we think of space as an empty stage where the drama of planets, stars and galaxies plays out. But in truth, that stage is alive. It is being built bigger and bigger while the performance continues. Because of this, something very strange happens. The farther away a galaxy is, the faster it seems to be rushing away. This is not because the galaxy itself is zooming at incredible speed, but because the space between us and that faraway galaxy is being stretched more and more. Some galaxies are so unimaginably distant, billions of light years away, that they appear to be retreating at astonishing speeds. And here comes one of the most mind-bending consequences. There are galaxies so far away that their light will never reach us. No matter how brightly they shine, no matter how long they exist, even if they send out light for billions upon billions of years, the space between us and them grows faster than light can cross it. It is as though the fabric of space itself is pushing them beyond our vision. That means the universe is full of galaxies that we will never see, no matter how powerful our telescopes become. These unreachable realms lie outside what scientists call the observable universe. The observable universe is the part from which light has had time to reach us since the universe first began, around 13.8 billion years ago. But do not worry. The expansion of space does not pull everything apart. The Earth is not drifting away from the Sun. Your chair is not slowly sliding away from your desk. On small scales, gravity is much stronger than expansion and holds things firmly together. In places like solar systems, entire galaxies, or even groups of galaxies, gravity wins the cosmic tug-of-war. The stretching of space only becomes obvious over enormous distances, millions or even billions of light years across. There is another twist that makes the universe even stranger. It has no center. There is no single point where the expansion began, no cosmic city from which everything is flying outward. Expansion happens everywhere, all at once. From any galaxy you choose, it looks as if all the other galaxies are moving away. Just like on that balloon, stand on any dot, and every other dot seems to drift away from you as the balloon grows. Astronomers looking through their telescopes see this exact effect. This was not an easy idea for scientists to accept. It is so different from how we experience motion in our everyday lives. On Earth, when something moves, it moves across a fixed background, like a car speeding down a road or a person walking across a field. But in the universe, even the background is not fixed. It is stretching beneath everything. It is as though the floor under your feet were lengthening while you walked, carrying you forward without you even noticing. The universe has not always expanded at the same gentle, steady pace. Over billions of years, the speed at which space itself stretches has shifted and changed. Right after the Big Bang, an enormous event that happened about 13.8 billion years ago, the universe went through a sudden, breathtaking burst of growth known as inflation. In less than a fraction of a second, space ballooned outward at an almost unimaginable rate. Though it lasted only for the tiniest moment, this event set the stage for everything that would follow. When inflation ended, the universe did not stop growing, but its expansion slowed down. At this stage, a new balance of forces came into play. On one side was the outward push left behind by the Big Bang, and on the other was gravity, the force that pulls matter together. For billions of years, the cosmos was shaped by this great tug-of-war. Expansion tried to stretch everything farther apart, while gravity tried to pull galaxies back together. This struggle determined much of the structure of the universe we see today. To measure how quickly the universe is stretching, scientists rely on a very important number called the Hubble constant. This constant describes how fast galaxies are moving away from each other, depending on how far apart they are. It is one of the most valuable tools in cosmology because it helps researchers figure out the age, size, and ultimate fate of the universe. The Hubble constant is measured in kilometers per second per megaparsec. A megaparsec is a special unit of distance that astronomers use, equal to about 3.26 million light-years. This means that if a galaxy is 1 megaparsec away, the Hubble constant tells us exactly how many kilometers per second it is moving away from us. The farther away a galaxy is, the faster it speeds off, and the Hubble constant captures this relationship. But getting the exact value of the Hubble constant is far more difficult than it sounds. It requires extremely precise measurements of both how far galaxies are and how fast they are moving away. To measure distance, astronomers often rely on special stars called Cepheid variables. Cepheid variables are like cosmic beacons. They pulse, growing brighter and dimmer at regular intervals, almost like the steady beat of a cosmic heart. What makes them so useful is that their pulse rate reveals their true brightness. By comparing how bright a Cepheid star actually is with how bright it looks from Earth, astronomers can calculate its distance with remarkable accuracy. Once the distance is known, the next step is to measure speed. This is done using redshift. When a galaxy races away from us, its light stretches out into longer, redder wavelengths, much like the sound of a siren lowering in pitch as an ambulance drives past. By measuring exactly how red the galaxy's light has become, astronomers can calculate how fast it is moving away. With both distance and speed in hand, the Hubble constant can be determined. In theory, this method seems straightforward, but in practice, things get tricky. Over the years, different research groups have found slightly different values for the Hubble constant. This disagreement has led to one of the biggest debates in modern astronomy, known as the Hubble tension. There are two main ways to calculate the Hubble constant, and they give slightly different answers. The first method looks at galaxies relatively close to us. Astronomers use Cepheid variables and exploding stars called supernovae as measuring sticks to determine both distance and redshift. This method usually gives a Hubble constant of about 73 kilometers per second per megaparsec. The second method looks much farther back in time, to the cosmic microwave background, the faint afterglow of the Big Bang itself. This ancient light is like a baby picture of the universe when it was only about 380,000 years old. By studying patterns in this glow and running complex computer models, scientists can estimate today's rate of expansion. But this method gives a lower value of around 67 kilometers per second per megaparsec. A difference of 6 kilometers per second per megaparsec may not sound like much, but in cosmology, it is huge. If our models of the universe were perfect, both methods would give the same result. The fact that they don't suggests that something is missing in our understanding. One possibility is that dark energy, the mysterious force pushing the universe apart, does not behave exactly as we expect. Or perhaps some exotic form of matter or energy existed in the early universe but vanished later on. Another possibility is that gravity itself behaves differently on the larger scales of the cosmos. Albert Einstein's theory of general relativity has passed every test in our solar system and within galaxies, but it has never been tested across the entire universe. If gravity weakens or changes over great distances, it could explain the mismatch in results. Some scientists have even proposed new versions of relativity to account for this mystery. Of course, it is also possible that the Hubble tension is not a problem with physics, but with the measurements themselves. Calculating distances in deep space is extraordinarily difficult, and even a small error in how we understand Cepheid variables or supernovae could cause big differences in the final number. Similarly, the models used to study the cosmic microwave background are extremely complex. If they are slightly off, the results for the Hubble constant would also be off. As time went on, the rate of expansion itself changed again. In the early universe, when everything was packed much closer together, gravity's pull was stronger and slowed expansion more effectively. But as galaxies drifted farther apart, gravity weakened. Then, about 9.8 billion years after the Big Bang, around 4 billion years ago, the expansion of the universe began speeding up once more, driven by dark energy. Today, astronomers are using powerful new tools to get closer to the truth. Instruments like the James Webb Space Telescope are providing clearer, sharper, and more accurate data than ever before. The hope is that with these advanced observations, scientists will one day solve the puzzle of the Hubble tension and discover the true value of the Hubble constant, unlocking even deeper secrets about how the universe began, how it has changed, and what its ultimate future might be. The way our universe expands raises one of the most exciting and puzzling questions in all of science. How does gravity, the invisible but powerful force that holds everything together, interact with the stretching of space itself on the biggest scales we can imagine? Right now, we know with certainty that the universe is expanding. What this really means is that galaxies, like glowing islands of stars, are drifting farther and farther apart because space itself is growing larger. But here's the surprising part. Even though space is stretching, galaxies themselves are not being ripped to pieces. Neither are clusters of galaxies. That's because gravity, which acts like the great glue of the cosmos, is working tirelessly to keep them bound together. So what we see is a grand cosmic tug-of-war. On one side is the expansion of space, pulling galaxies away from each other. On the other side is gravity, pulling things back together. The balance of this struggle shapes the universe we see and live in today. Gravity, as explained in Albert Einstein's groundbreaking theory of general relativity, is the mysterious force that causes objects to attract one another. It's the reason why planets faithfully circle around stars, why stars clump together into galaxies, and why galaxies themselves gather into even larger communities called clusters. Without gravity, the universe would be nothing more than a scattered fog of atoms and particles drifting without order. There would be no stars to shine, no planets to walk upon, and no galaxies to gaze at. Just a shapeless, lonely sea of matter. Einstein showed us that gravity is not some invisible rope or chain, but rather the bending of space and time itself. Anything with mass, whether it's a grain of sand, a planet, or a star, warps the fabric of space-time, creating a kind of invisible dip that draws other objects toward it. The heavier something is, the deeper its dip and the stronger its pull. But here's where things get even more fascinating. While gravity is holding things tightly together on small and medium scales, the universe itself is still expanding on the very larger scales. And this expansion doesn't work like cars driving down a road or rockets blasting through empty space. Instead, it's space itself that stretches, and galaxies are carried along with it, like raisins floating inside a loaf of bread that is slowly rising in the oven. This stretching only becomes obvious when we look across truly vast distances, millions or even billions of light years. On smaller scales, such as within a galaxy or a small group of galaxies, the grip of gravity is far stronger than the gentle tug of expansion. That is why galaxies do not get stretched thin or torn apart by the growing universe. The stars inside them, along with the mysterious substance called dark matter, are packed closely enough that their combined gravity completely overwhelms the tiny effect of expansion. Take our own Milky Way galaxy as an example. Its closest large neighbour, the Andromeda galaxy, is not drifting away because of expansion. Quite the opposite. The two are moving toward each other. Their gravity is so strong that it overpowers the expansion of space in their region. In about 4 billion years, the Milky Way and Andromeda will collide in a slow, magnificent cosmic dance, eventually merging into one enormous galaxy. This is why scientists say that expansion only truly matters on the largest possible scales, across the giant gulfs of space that separate clusters of galaxies from one another. Inside clusters, where hundreds or even thousands of galaxies swirl together, gravity still dominates. These clusters are among the most massive structures in the entire cosmos, and gravity is the thread that binds them. Yes, the space between clusters continues to expand, but the galaxies within a cluster remain locked together, orbiting a common centre of mass, like bees buzzing tirelessly around a hive. But what about the far future? If the expansion of the universe continues to speed up, as many scientists believe, what will happen then? The driving force behind this acceleration is something strange and unseen, which we call dark energy. Unlike gravity, which pulls things together, dark energy acts like a push, forcing the universe apart. If dark energy grows stronger and stronger, it may one day overpower gravity completely. In this case, even the mighty pull of gravity will not be able to hold stars, galaxies, or even atoms together. Some scientists imagine a dramatic end known as the Big Rip. In this terrifying scenario, dark energy would tear apart galaxy clusters, then galaxies themselves, then stars and planets, and finally even the atoms that make up matter. The universe would become a cold, empty desert of isolated particles drifting endlessly in the dark. But for now, gravity still rules in many places. It keeps stars spinning gracefully within galaxies, galaxies dancing inside clusters, and clusters forming part of the cosmic web that stretches across the universe. The balance between expansion and gravity continues to shape everything we see in the night sky. As the universe keeps growing larger and larger, its enormous structures are also changing in ways that are both fascinating and dramatic. These colossal formations, like clusters of galaxies, long threads of matter called filaments, and vast empty spaces known as voids, did not just appear by chance. They were slowly built over billions of years, as gravity gently pulled matter together, weaving a vast, intricate network. Galaxies are linked along these invisible threads made of dark matter, the mysterious substance we cannot see, and ordinary matter, the stuff that makes up stars, planets, and everything we are familiar with. Yet gravity is only one side of the story. While it tries to gather galaxies together, there is another force at work, quietly tugging them apart: the steady expansion of space itself. This creates a cosmic tug-of-war on a scale almost impossible to imagine. On one side, gravity strives to hold things together. On the other, space stretches relentlessly, carrying galaxies farther and farther from one another. Over time, this expansion is creating ever larger gaps between galaxies and the cosmic structures that contain them. The very fabric of the universe is being stretched, reshaping its larger structures in ways we can barely comprehend. Scientists call the overall arrangement of all these structures the cosmic web. Picture a giant three-dimensional web made of galaxies. The long threads of this web are called filaments, dense highways of galaxies connecting enormous clumps called galaxy clusters. In between these filaments lie enormous empty regions, the voids, where very few galaxies exist at all. But this cosmic expansion is not uniform. Inside galaxy clusters, gravity is strong enough to keep the galaxies close together. Even as space itself stretches, these galaxies remain bound, moving together like members of a tight-knit community. In the enormous stretches between clusters, however, gravity is too weak to resist the expansion. There, space keeps growing, causing voids to swell and filaments to stretch thinner with time. This gradual process is called cosmic drift. Galaxies that were once neighbours slowly move apart. In the early universe, collisions and mergers between galaxies were common. These dramatic encounters shaped the galaxies we see today. But now, as the universe grows emptier, such interactions are becoming rare. Galaxies drift alone, rarely exchanging gas, dust, or stars, and the cosmos grows quieter, calmer, and lonelier. Among the most striking consequences of this expansion is the growth of voids. These immense empty regions continue to grow larger and more dominant, making the overall structure of the universe more spread out and fragmented. In the far future, the cosmos may resemble a dark, silent ocean, dotted only with tiny glowing islands, the galaxy clusters that remain tightly bound by gravity. Even as space stretches, galaxies inside clusters are likely to stay together, held by their mutual gravitational pull. But outside these clusters, nothing can prevent the universe from expanding. Today, filaments still connect galaxy clusters, but these links are weakening. Eventually the threads will stretch so far that they break, and galaxies along them will drift apart, isolated and alone. Over billions and billions of years, each cluster will become an island in a sea of emptiness. From the viewpoint of a single galaxy, only the few nearby galaxies in the same cluster will be visible. All others, scattered across the ever-growing voids, will vanish from sight, not because they have disappeared, but because the light they emit will be stretched so far by the expansion of space that it will become invisible. Scientists call this phenomenon redshifting. In extreme cases, light is stretched into wavelengths that are completely undetectable, leaving future astronomers in a tiny cosmic bubble of visible galaxies, with the rest of the universe hidden behind an invisible curtain. As this process continues, the creation of new galaxies slows and eventually stops. In the early universe, galaxies formed from clouds of gas and dark matter collapsing under gravity. But as matter spreads thinly across the expanding cosmos, there is less available to form new stars or galaxies. Existing galaxies will continue evolving slowly, but the birth of entirely new galaxies will cease. Over unimaginable time, galaxies will drift farther apart until even their light can no longer bridge the immense distances between them. The universe will become darker, quieter, and more isolated than ever. All of this also raises a fascinating question. Could the stretching of space itself influence the way we experience time? Time and space are not separate entities. They are intertwined into a single fabric called space-time, as described by Einstein's theory of general relativity. When space bends, stretches, or warps around massive objects like stars or black holes, time itself can slow down. Experiments have confirmed this effect. So, does the expansion of the universe affect time in a noticeable way? For our everyday lives on Earth, the answer is no. Time seems steady and unchanging. Our clocks tick reliably, the Earth continues its yearly orbit around the Sun, and sunrise and sunset happen on schedule. Cosmic expansion does not interfere with our day-to-day experience of time, yet on enormous cosmic scales, across millions or billions of light years, the link between space and time becomes profound. In the vast, sparsely populated regions between distant galaxies, where gravity is weak and expansion dominates, the stretching of space starts to influence both light and time. As space expands, it stretches the light travelling through it. This is called redshift. Imagine light waves as ripples on a pond. When the pond stretches, the ripples lengthen and slow down. Light from distant galaxies behaves the same way. It stretches, shifting toward the red end of the spectrum. But this stretching affects more than just colour. It also subtly alters how we perceive time from those galaxies, linking the expansion of space directly to the flow of time itself. The farther away a galaxy is from us, the more its light appears stretched, and the longer it seems to take to reach our eyes. It's almost as if time itself is moving more slowly in those distant parts of the universe. When we observe a supernova, a star that explodes in a brilliant flash, billions of light years away, it seems to unfold in slow motion. The explosion takes longer to play out than it would if it happened in our cosmic neighbourhood. This strange and fascinating effect is known as time dilation, and it happens because the universe itself is stretching and expanding. When we look at the farthest reaches of the observable universe, we're not just looking across immense distances in space, we're also peering deep into the past. The light from those regions has travelled for billions of years to reach us. But because the universe has been expanding during that journey, this ancient history seems to move in slow motion. The stretching of space not only elongates the light waves, but also stretches the actual flow of events. A cosmic event that might last only a few seconds nearby could appear to take much, much longer if it occurred billions of light years away. Some scientists think that as the universe continues to expand, and at an ever faster rate, time itself might behave in even stranger ways. One possibility is a scenario called the Big Freeze, or heat death. In this vision of the distant future, all stars will eventually burn out, galaxies will drift far apart, and the universe will become a cold, dark, and lifeless place. Without stars shining or energy flowing, time might lose its meaning. If nothing is changing, if no events are happening, then there would be nothing left to mark the passage of time. In a sense, time itself could come to a complete stop. According to Albert Einstein's theory of general relativity, time is not fixed like the steady ticking of a clock. Instead, it is relative. It can flow at different speeds depending on gravity and motion. For instance, near a massive object such as a black hole, time slows down. This phenomenon, known as gravitational time dilation, has been tested and confirmed by scientists using extremely precise clocks placed on airplanes and satellites. The clocks tick just a little more slowly in stronger gravitational fields. Could something similar happen on a cosmic scale? Could the stretching of space affect the flow of time across the entire universe? Scientists are still exploring these questions. We do know that dark energy, the mysterious force driving the universe's accelerated expansion, changes how we observe time across vast distances. But how it might influence the passage of time in the far future remains a deep mystery. Some physicists even wonder if time, as we perceive it, is not a fundamental property at all. Perhaps time is an emergent phenomenon, a result of deeper, hidden processes in the universe. It could arise from the interactions of space, matter, and energy, rather than existing independently. This idea is still speculative, but it opens up exciting possibilities about the true nature of time. Now let's consider another question. If space is expanding, does this growth affect the tiniest components of the universe as well? What happens at the quantum level, where particles like electrons and protons exist? At its heart, the expansion of the universe means that the space between galaxies and galaxy clusters grows larger over time. Yet inside galaxies, and especially within stars, planets, and atoms, the expansion of space hardly matters. The forces that hold these smaller structures together are far stronger than the gentle stretching of cosmic space. Inside atoms, for example, tiny particles are held tightly together by powerful forces. The electromagnetic force keeps electrons orbiting the nucleus, while the strong nuclear force holds the nucleus itself together. The strong nuclear force is roughly 100 times stronger than electromagnetism and millions of times stronger than gravity. These forces are what hold the building blocks of matter in place. This means that the atoms in your body do not stretch, the molecules in the air do not drift apart, the rocks under your feet remain solid. Even whole planets and stars do not feel the universe expanding. The expansion is only noticeable across the vast, nearly empty spaces between galaxies, not within them. This illustrates just how powerful these small-scale forces are. They easily overpower the weak push of cosmic expansion. In our everyday lives, we are unaffected. Everything we see and touch is held firmly together by these fundamental forces. Still, scientists ask whether the expansion of the universe could have any influence in the quantum realm. At first, the answer seems to be no. But a deeper look reveals intriguing connections that hint at a profound link between the very small and the cosmic scale. One connection comes from quantum fluctuations. According to quantum theory, the set of rules describing the tiniest scales of the universe smaller than atoms, even empty space is not truly empty. It is filled with energy, constantly bubbling with tiny particles that appear and vanish in the blink of an eye. These events happen all the time, but they are so brief and small that we do not notice them in daily life. Yet some scientists believe that these minuscule fluctuations played a crucial role in shaping the universe. Shortly after the universe was born, around 13,800,000,000 years ago, it underwent a period of cosmic inflation. During this incredible moment, which lasted only a tiny fraction of a second, the universe expanded unbelievably fast. Far faster than the speed of light. In less than the blink of an eye, space stretched from something smaller than a single atom to a size possibly spanning galaxies. Here is the fascinating part. During this inflation, those tiny quantum fluctuations were stretched along with space. These minute ripples in energy were pulled and expanded, eventually becoming the seeds for galaxies, stars, and the vast cosmic structures we observe today. In other words, phenomena on an invisible microscopic scale helped shape the grand universe we inhabit. The enormous cosmos around us may have its roots in the mysterious quantum world. Another possible connection between cosmic expansion and quantum theory involves dark energy. Scientists think that dark energy is what causes the universe to keep expanding at an ever faster rate. Some theories suggest that dark energy itself may originate from the quantum realm. If that is true, then the growth of space on the larger scales could be closely tied to events at the tinier scales, linking the grand and the microscopic in ways we are only beginning to understand. The story of how our universe grows and stretches is far from ordinary. It does not begin with a gentle, steady expansion of space. Instead, right after the event we call the Big Bang, something wild and almost unbelievable took place. A sudden, lightning-fast surge of growth known as cosmic inflation. This burst of expansion was incredibly brief, lasting for less than 1/1,000,000,000th of a second, but its impact was enormous. Even though it happened in the blink of an eye, it shaped the universe forever. In those very first sparks of time after the Big Bang, the universe was unimaginably hot and tightly packed. It was filled with a dense mix of tiny particles and pure energy, a glowing, chaotic soup of creation. Then, almost instantly, space itself began to stretch at a speed far greater than anything we can witness today. Within that minuscule window of time, the universe ballooned from something smaller than a single atom to something that spanned distances measured in light years. And all of that astonishing growth happened in less than 1 second. This sudden expansion smoothed out the young universe. It erased the worst clumps and rough patches, leaving behind a surprisingly balanced and even structure. Yet, tiny ripples in density remained, slight bumps and dips that were almost invisible. These faint irregularities would later become the seeds from which galaxies, stars, and eventually planets would grow. Without this extraordinary moment of inflation, the universe might have been too messy and uneven to ever form the grand cosmic structures that we now see, or to support the rise of life itself. Thanks to inflation, the universe became vast, mostly smooth, and yet just varied enough to allow stars, galaxies, and even living beings to emerge. Inflation set the stage for the slower, steadier expansion that has been continuing ever since, shaping the cosmos into the breathtaking structure we see today. For a long time, scientists assumed that this cosmic expansion would eventually slow down. That seemed logical since gravity, the pull from galaxies, stars, and matter, should tug everything back together, at least a little. But then came a surprise. In the late 1990s, 2 independent teams of astronomers studied a special type of exploding star called a supernova. These cosmic fireworks, which occur when certain stars die, shine so brightly that they can be used as cosmic measuring sticks. By observing distant supernovae, the astronomers hoped to learn how the universe's rate of expansion had changed over time. The results were shocking. The supernovae appeared dimmer than expected, which meant they were farther away than they should have been if the expansion was slowing down. The conclusion was unavoidable. Instead of slowing, the universe's expansion was speeding up. To explain this mystery, scientists proposed the existence of dark energy, a strange, invisible force that pushes galaxies apart and overcomes gravity. Today, astronomers believe that dark energy makes up about 70% of all the energy in the universe. Yet the true nature of dark energy remains one of the greatest unsolved puzzles in science. Unlike ordinary matter, which clumps together into stars and planets, or dark matter, which gathers around galaxies, dark energy does not cluster at all. Instead, it appears evenly spread throughout space. Even more puzzling, as space expands, dark energy does not thin out. It continues to fill the new space, as if it is built into the very fabric of the cosmos. Some theories even suggest that dark energy is a natural feature of space itself. As more space is created, more dark energy appears, fueling even faster expansion. It is like a snowball rolling down a hill. The more it grows, the faster it rolls. One explanation links dark energy to something known as the cosmological constant, an idea first introduced by Albert Einstein in his theory of general relativity. At the time, most scientists thought the universe was static, neither expanding nor shrinking. So Einstein added the cosmological constant to his equations to make the math work. But when Edwin Hubble later discovered that the universe was expanding, Einstein abandoned the constant and even called it his biggest mistake. Now, with the mystery of dark energy, that old idea has returned. Some scientists believe the cosmological constant may be real after all, woven into the fabric of space itself. This strange discovery has raised deep questions about the universe's future. If expansion keeps speeding up, what will the far-off future look like? One possibility is called the Big Freeze. In this scenario, galaxies will drift farther and farther apart, stars will burn out, and the universe will slowly grow cold, silent, and dark. Another, even more dramatic idea is the Big Rip. If dark energy grows stronger over time, it could eventually tear apart galaxies, stars, planets, and even the atoms themselves. Everything would be ripped to pieces by unstoppable expansion. Right now, we know that dark energy is the dominant force in the universe. Scientists estimate that about 68% of everything in the cosmos is dark energy. Dark matter, another mysterious ingredient, makes up about 26%. The matter we are most familiar with, the stars, planets, and all the things we can actually see, only adds up to about 5%. Other forms of energy, such as light particles, photons, and ghostly particles called neutrinos, are so small in comparison that they barely count. Even though dark energy has an extremely low density, roughly 7 times 10 to the power of negative 30 grams per cubic centimeter, it still rules the universe. This is because it is spread evenly across all of space, filling every corner of the cosmos no matter where you go. The first evidence for dark energy came from those very same exploding stars, type Ia supernovae. These stars shine with a consistent brightness, so astronomers can use them as cosmic rulers. By studying the stretching of their light, a phenomenon called redshift, scientists learned how fast they were moving away. To their surprise, the universe was not slowing down as expected, but racing apart faster and faster. That mysterious force became known as dark energy. There are still many theories about what dark energy really is. The leading explanation remains the cosmological constant, the idea that dark energy is the energy of empty space, an unchanging force that has always been part of the universe. Whether that is the full truth or just the beginning of a deeper mystery, one thing is certain: dark energy holds the key to the fate of the cosmos. Another possible explanation is that dark energy comes from scalar fields, a kind of energy that changes with time and across space. These fields might act differently in different areas of the universe, making dark energy more changeable. Some versions of this idea include quintessence and moduli fields. Other ideas suggest that dark energy could interact with gravity in unknown ways. One idea, called cosmological coupling, says that dark energy and gravity might be linked in a way we do not yet understand. Another idea, called interacting dark energy, says that dark energy might be affected by other invisible forces in the universe. The idea of a strange energy filling space actually goes back to Albert Einstein. In the early 20th century, Einstein added something called the cosmological constant, lambda, to his equations of general relativity. At that time, scientists thought the universe was unchanging, not growing and not shrinking. To make his equations fit this belief, Einstein added the cosmological constant, which acted like a force that pushed against gravity and stopped the universe from collapsing inward. But in the year 1929, the astronomer Edwin Hubble found that the universe was not fixed at all. It was growing larger. This showed that Einstein's first idea was wrong. He later called the cosmological constant his biggest mistake. Strangely, many decades later, scientists found that a repelling force, what we now call dark energy, was really pushing the universe apart. This meant that Einstein's idea may not have been a mistake after all. In the year 1980, physicists Alan Guth and Alexei Starobinsky suggested a new idea called cosmic inflation. This idea says that just after the Big Bang, the universe went through a very short but extremely fast growth, expanding at an unbelievable speed. This inflation shaped the universe and explains why galaxies are spread out the way we see them today. Inflation looks similar to dark energy, because both make space expand very quickly. But the energy behind inflation was far stronger than the dark energy we see today. Scientists are still trying to learn whether these two are related or completely separate. By the 1980s, scientists had created models of the universe that depended on cold, dark matter, a kind of dark matter that moves slowly compared to light. These models explained how galaxies formed, but they did not match every detail. For example, they predicted a slower Hubble constant, the rate at which the universe grows, than what astronomers actually measured. Things changed in the year 1992, when NASA's COBE spacecraft found tiny differences in the cosmic microwave background, the faint glow left over from the Big Bang. This discovery forced scientists to rethink their models. A big breakthrough came in the year 1998, when astronomers studying faraway supernovae found clear proof that the universe's growth was speeding up, not slowing down. This was the first direct evidence that dark energy was real. More findings followed. In the early 2000s, experiments like Boomerang and Maxima studied the cosmic microwave background and showed that the total energy of the universe was almost exactly equal to the critical density, the amount needed to make the universe flat on a large scale. But when scientists measured the amount of matter, they found it was only about 30% of this critical density. The missing energy was explained as dark energy. More proof came in the year 2001 from the 2-degree field galaxy redshift survey, which studied how galaxies are spread out and showed that dark energy was needed to explain the results. Then, from the year 2003 to 2010, NASA's WMAP satellite gave even more exact measurements of the cosmic microwave background, confirming the lambda cold dark matter model as the best explanation of how the universe formed and changed. The term dark energy was first used in the year 1998 by physicist Michael S. Turner, following the earlier phrase, dark matter, which had been introduced by Fritz Zwicky in the 1930s. Even with all these discoveries, dark energy is still one of the greatest mysteries in physics. Some scientists think it could be a built-in property of space itself. Others think it may be tied to quantum mechanics, the strange rules that guide particles at the smallest levels. Future experiments such as new space telescopes and large galaxy surveys aim to reveal more about this mysterious force. To truly understand how the universe grows over time, scientists need to measure its expansion with incredible accuracy. In general relativity, researchers figure out the speed of expansion by looking at the universe's shape and using an idea called the cosmological equation of state. This explains how things like temperature, pressure, and the combined amounts of matter, energy, and vacuum energy affect space. One of the hardest challenges in modern cosmology is finding out the equation of state for dark energy. Scientists believe dark energy plays a huge role in making the universe expand faster, but its real nature is still unknown. To study it, researchers use the cosmological constant in the Standard Model of Cosmology, also called the Friedmann-Lemaitre-Robertson-Walker metric. This creates what is known as the lambda cold dark matter model, often called the gold standard of cosmology, because it matches real observations very closely. Since the year 2013, the lambda cold dark matter model has been tested again and again with very exact observations, including data from the Planck spacecraft and the Supernova Legacy survey. Early results from this survey suggested that dark energy acts almost exactly as Einstein's cosmological constant predicts, with an accuracy of about 10%. More recent findings from the Hubble Space Telescope's Higher Z team show that dark energy has been at work for at least 9 billion years, long before the universe began its rapid speeding up. But even with all these results, dark energy is still one of the biggest puzzles in physics. It seems to be very smooth and spread evenly across space, with an incredibly low density. Unlike matter or energy that we normally know, it does not appear to interact with anything except gravity. Its density is amazingly tiny, about 1 divided by 10 followed by 27 zeros kilograms in every cubic meter, making it nearly impossible to measure directly in a laboratory. Yet, despite being so faint, dark energy makes up about 68% of the total energy in the universe. This is because, unlike matter, which clumps together, dark energy spreads evenly across all of space, strongly affecting how the universe grows. One of the main explanations for dark energy connects it to something called vacuum energy. This means the tiny changes of particles and antiparticles that constantly appear and disappear in empty space, following Heisenberg's uncertainty principle. According to Einstein's relativity, this vacuum energy should also affect gravity, which means it adds to the cosmological constant. Scientists believe this is one of the main reasons the universe is expanding faster. But there is a huge problem. When physicists use quantum field theory to calculate how much vacuum energy should exist, they get a number much larger than what is actually seen. This massive difference between theory and reality remains one of the biggest unsolved problems in physics today. No matter what dark energy really is, for it to drive the faster expansion of the universe, it must have a very strong negative pressure. In general relativity, pressure works like mass when it comes to gravity. Both pressure and mass are part of something called the stress-energy tensor, which explains how matter and energy affect gravity. For dark energy, this negative pressure pushes against gravity, making space expand more quickly. If the universe was shrinking instead, this same pressure would slow that shrinking down. This effect is sometimes called gravitational repulsion because it pushes things apart, working against the usual pull of gravity. When we look at the universe's main parts, we see that everything falls into 3 big groups: matter, radiation, and dark energy. Matter includes everything with mass, from stars and planets to tiny grains of dust. As the universe expands, the density of matter goes down in proportion to the cube of the expansion factor. For example, imagine a box filled with particles. If the box doubles in size, the energy of the particles inside does not just get cut in half, it drops by a factor of 8 because the volume grows in 3 dimensions. Radiation, which includes light and heat, behaves differently. As space grows, the energy of radiation goes down even faster than matter. This happens because besides spreading out, the light waves themselves get stretched. This stretching, called redshift, makes radiation lose energy more quickly than matter. Dark energy, however, acts in a totally different way. Unlike matter and radiation, its density does not drop as the universe grows. Instead, it stays the same no matter how large space becomes. This means that while matter and radiation thin out over time, dark energy stays steady, filling all of space and driving the universe's faster expansion. Scientists have gathered many clues that dark energy exists, even though it has not been directly detected. Distance and redshift studies. By looking at how light from faraway objects has been stretched, scientists found that the universe has expanded faster in recent times than it did earlier. This points to something, probably dark energy, causing the speed up. The need for extra energy. The universe appears to be flat, meaning it does not curve inward or outward. For it to be flat, the total energy must be at a certain level. Since visible matter and dark matter are not enough, dark energy must provide the missing amount. Patterns in cosmic structures. When scientists look at how galaxies and large cosmic structures are arranged, they find patterns that point to dark energy. The spread of galaxies across space gives more clues about how the universe is expanding and what force is driving it. In the year 1998, a group of skywatchers known as the High-Z Supernova Search Team made a shocking finding while studying a special kind of exploding star called Type Ia supernovae. They thought they would see that the universe's expansion was slowing down because of gravity, but instead they saw the opposite. The universe was actually expanding faster and faster. Just 1 year later, in 1999, another group of researchers, the Supernova Cosmology Project, reached the same surprising result. Their important work reshaped our understanding of the universe and earned them the well-known Nobel Prize in Physics in the year 2011. Since then, many other studies have strengthened this finding. Observations of the cosmic microwave background, weak light left over from the Big Bang, have given strong proof. Also, skywatchers have studied how light bends around heavy objects in space, an effect called gravitational lensing, and have looked at the large-scale shape of the universe. All these results support the idea that a strange force called dark energy is driving the universe's faster expansion. Some doubters say that the strongest proof comes only from looking at redshift, the way light stretches as objects move away, and the distances of supernovae. But other evidence, such as patterns in the cosmic microwave background, also shows that the universe is expanding faster than it would without dark energy. Supernovae are very useful for studying the universe because they work like natural measuring tools, often called standard candles. Scientists know exactly how bright these blasts should be, which lets them measure how far away they are. By comparing the distance of a supernova with how much its light has stretched, its redshift, skywatchers can carefully track how fast the universe is expanding. Type Ia supernovae are especially valuable because they always explode with the same brightness, making them some of the most dependable cosmic markers. Recent studies show that dark energy makes up about 71% of the universe, while the other 29% is made of dark matter and normal matter. The leading idea that explains how galaxies, stars, and other cosmic structures form suggests that matter only makes up about 30% of the universe's total critical density, the amount needed for the universe to be flat in shape. More proof of dark energy came in the year 2011 from the Wiggle-Z Galaxy Survey, which studied more than 200,000 galaxies. Researchers used a new method to measure distances to galaxies as far as 2,000 million parsecs away. Their results showed again that the universe has been expanding faster and faster, giving even stronger support for cosmic acceleration. For the universe to be as flat as it looks, there must be some extra kind of energy filling space. All the visible matter, both regular and dark, makes up only about 30% of what is needed. The other 70% is thought to be dark energy. Data from the Wilkinson Microwave Anisotropy Probe, a spacecraft that mapped the early universe, estimated that dark energy makes up about 73% of the universe. Later results from the Planck satellite gave a more exact number, showing that dark energy makes up about 68%, while dark matter makes up about 27%, and regular matter makes up just under 5%. Dark energy also helps explain unusual patterns in the cosmic microwave background. When light particles, called photons, travel through areas of strong gravity, such as galaxy clusters or wide empty spaces, they lose or gain energy. This effect causes temperature changes in the background radiation and is called the integrated Sachs-Wolfe effect. It is seen as another major clue pointing to the presence of dark energy. Scientists have also started using a new way to study dark energy by measuring the Hubble constant, which describes how the universe's expansion rate changes over time. They focus on galaxies that have grown in a steady way, using them as cosmic clocks. By studying their ages and redshifts, researchers can estimate how fast the universe was expanding at different times in history. Even with all this proof, dark energy is still one of the biggest unsolved puzzles in physics. Scientists agree it is very important for the universe's faster expansion, but they still do not fully understand what it is or how it works. To find answers, researchers are testing many ideas. Some are checking Einstein's theory of gravity to see if changes are needed. Others are trying to uncover the exact traits of dark energy, while some are even thinking about other possible explanations based on unusual cosmic findings. One of the simplest ideas about dark energy is that it is a basic feature of space itself. In this view, even totally empty space contains a type of energy, often called vacuum energy. This idea is known as the cosmological constant and is shown by the Greek letter lambda. It is the base of the lambda CDM model, which is now the most widely accepted explanation of the universe's shape. Since Einstein's famous equation shows that energy and mass are linked, this vacuum energy should have a pull shaping how the universe expands. But there is a big problem with this idea. Calculations from quantum physics suggest that the amount of vacuum energy should be unbelievably huge, about 120 orders of magnitude larger than what is seen. If that were true, the universe would have expanded so quickly that galaxies, stars, and planets could never have formed. Yet we live in a universe where such structures do exist. Something must be balancing out most of this energy, but not all of it. Scientists still do not know why, making dark energy one of the hardest puzzles in modern physics. While many believe dark energy is a constant, unchanging force, some scientists think it could be something far more active, an energy field that changes over time. This idea is called quintessence. Unlike the cosmological constant, which is the same everywhere, quintessence acts like an energy field spread across the universe, affecting its expansion in different ways at different times. It is thought to be very light so that, unlike normal matter, it does not clump into stars and galaxies. Some versions of this idea suggest that the universe's expansion is happening a little slower than the standard model predicts, but there is still no clear proof to confirm or deny this idea. One of the biggest open questions about dark energy is why it became so important at this moment in the universe's history. If it had taken over too early, the universe's fast expansion could have stopped galaxies from forming, and life as we know it might never have come to be. Some scientists think this is only chance, while others think it supports a debated idea called the anthropic principle. The thought that the universe must be the way it is because we are here to see it. Some quintessence models have a built-in system, called a tracker, that naturally explains why dark energy became important at this time. In these models, dark energy's behavior is tied to the amount of radiation in the early universe, which could explain its late but powerful rise. Some extreme versions of quintessence suggest even stranger outcomes. One of these is phantom energy, a type of dark energy that grows stronger over time instead of staying the same. If this is true, the universe would not just keep expanding, it would end in a frightening event called the Big Rip. In this end, the force of expansion would grow so strong that it would first tear apart galaxies, then stars, then planets, and finally even atoms themselves, leaving nothing. Another version of quintessence, called K-essence, suggests that dark energy might be made of unusual forms of energy that behave in ways never seen before. Some versions of K-essence even suggest the existence of negative kinetic energy, which could have strange and unpredictable effects on how the universe changes. In recent years, skywatchers have found disagreements in the measurements of the universe's expansion rate. This problem, called the Hubble tension, suggests that the standard model of the universe may be missing something important. Some researchers think that only special kinds of quintessence, with extra effects, can explain this mismatch. Even though dark energy is still one of the greatest mysteries in physics, it is deeply tied to Albert Einstein's theory of general relativity. Some scientists say that if general relativity were changed in certain ways, we might not need dark energy at all to explain the universe's faster expansion. Many other theories have been suggested, but so far none have been fully proven. In fact, an important finding, the detection of gravitational waves from the event known as GW 170817, has already ruled out many of these changed gravity theories. According to space scientist Ethan Siegel, while other ideas about dark energy often make news, most experts still believe dark energy is real. Other theories do not match the observations as well as the current model does. Scientists think that the universe's expansion began speeding up about 5 billion years ago. Before that, gravity, mainly from dark matter and normal matter, was slowing things down. But as the universe grew larger, dark matter spread out and became less powerful, while dark energy stayed almost the same. In time, dark energy took over, making expansion speed up. Each time the universe doubles in size, the amount of dark matter in a space is cut in half, but dark energy stays nearly unchanged. What happens next depends on the nature of dark energy. If it stays constant, like the cosmological constant suggests, the universe will keep expanding forever. Distant galaxies will move away faster and faster until they go faster than light itself. This does not break the rules of physics, because space itself is stretching, not the galaxies moving through space. At present, scientists think that the cosmological event horizon, the distance past which we can never receive light or signals, is about 16 billion light-years away. If something happens within that range, its light might still reach us far in the future. But anything beyond that distance will be lost to us forever. As galaxies near this horizon, the light they give off will stretch into longer and longer waves, until it becomes invisible. To an observer in the far future, those galaxies will seem to fade away, until only our own local group of galaxies remains in an otherwise empty universe. While the thought of an endlessly expanding, dark and empty universe is unsettling, some other theories suggest more dramatic ends. If dark energy keeps getting stronger, the Big Rip could truly happen, tearing apart everything. But there are also theories that dark energy might change over time, maybe even reversing its effect. In that case, the universe could stop expanding and begin shrinking in a big crunch, collapsing back into a single point, which might lead to another Big Bang and the birth of a new universe. Another possibility is that dark energy works in cycles, making the universe expand and contract in an endless loop of Big Bangs and big crunches. Dark matter is a mysterious and invisible kind of matter that we cannot see because it does not interact with light or any other kind of radiation. We know it exists not by seeing it directly, but by observing its strange effects on gravity. These effects cannot be fully explained by the usual laws of physics unless there is much more matter in the universe than what we can actually detect. We notice dark matter's influence when we study the formation and evolution of galaxies when light bends around massive objects, a phenomenon known as gravitational lensing, and even in the way galaxies move within clusters. Its presence also shows up in the large-scale structure of the universe and in the faint leftover radiation from the Big Bang. In the most widely accepted picture of the universe, called the lambda CDM model, all the mass and energy of the universe is divided roughly like this. 5% is regular matter, 26.8% is dark matter, and 68.2% is dark energy. This means that dark matter alone accounts for nearly 85% of all the mass in the universe, and together with dark energy, it makes up about 95% of the total energy in the cosmos. Despite decades of research, scientists still do not know exactly what dark matter is. It seems to interact with ordinary matter and light only through gravity, which makes it extremely difficult to detect with current instruments. One leading idea is that dark matter is made of tiny unknown particles, such as weakly interacting massive particles, known as WIMPs, or Axions. Another possibility is that dark matter is composed of ancient black holes that formed in the earliest moments of the universe. Dark matter is classified according to how fast its particles move: cold, warm, or hot. Most scientists think that dark matter is cold, meaning that its particles move slowly. This slow movement allows dark matter to clump together over time, forming structures that help shape galaxies and clusters. While the majority of astrophysicists are convinced that dark matter exists, a small number of scientists remain skeptical. Some of them have observed phenomena that ordinary dark matter cannot fully explain. These scientists have proposed that perhaps our understanding of gravity needs to be adjusted. They have suggested alternative theories, such as modified Newtonian dynamics or new kinds of gravity, but none of these ideas can perfectly account for all the evidence. This suggests that, even if gravity requires some refinement, dark matter still seems to play a crucial role in the universe. The story of dark matter has a long and fascinating history, filled with discoveries and ideas from some of the brightest scientific minds. It begins in the late 19th century. In 1884, William Thomson, better known as Lord Kelvin, made intriguing observations about the number of stars surrounding the Sun. In a book based on lectures he gave in Baltimore, Kelvin estimated how stars moved near our solar system and speculated what might happen if there were 1 billion stars within 1 kiloparsec of the Sun. At that distance, stars would move in ways that were difficult to explain, hinting at the possibility of invisible matter in space. Lord Kelvin also estimated the Sun's age to be between 20 and 100 million years, a number later found to be far too low, but his curiosity about the movements of stars helped spark early ideas about dark matter. About 2 decades later, in 1906, the French mathematician and physicist Henri Poincaré introduced the term dark matter, or matière obscure, while discussing Lord Kelvin's work. Poincaré suggested that there might be hidden mass in the universe, though he believed it was less than the amount of visible matter. While his ideas were not entirely correct, his mention of dark matter brought the concept into scientific discussion. In the 1920s, astronomers continued to explore the idea of dark matter. In 1922, Dutch astronomer Jacobus Kapteyn was among the first to use the speeds of stars to suggest that some invisible mass might exist. He noticed that the motion of stars seemed influenced by unseen forces, hinting at hidden matter. Then, in 1930, Swedish astronomer Knut Lundmark expanded on this idea, realizing that the universe must contain much more mass than what telescopes could detect. This was an important step, showing that the visible universe might not tell the whole story. In 1932, Dutch astronomer Jan Oort studied the movement of stars near our galaxy and suggested that dark matter could exist in the galactic neighborhood. He concluded that our galaxy must contain more mass than we can see. Later, Oort realized that his measurements were not fully accurate, and more research would be needed to uncover the true nature of this invisible mass. Then, in 1933, Swiss astrophysicist Fritz Zwicky made a major breakthrough while studying galaxy clusters at the California Institute of Technology. He examined the Coma cluster, a large collection of galaxies, and found something surprising. The galaxies were moving much faster than expected based on the visible mass alone. Zwicky proposed that there must be a huge amount of invisible mass, which he called Dunkel Materie. He estimated that the Coma cluster had about 400 times more mass than could be seen through telescopes. This unseen mass, he suggested, was responsible for the gravitational force holding the galaxies together. Although Zwicky's numbers were off because of outdated data, he was one of the first to recognize that the universe contains invisible mass exerting gravity. Zwicky thought dark matter was ordinary matter that simply did not emit light, unlike today's view that dark matter is something entirely different and mysterious. Nevertheless, his work marked a crucial step toward our current understanding. Over the following years, more evidence for dark matter began to appear. In 1939, H.W. Babcock studied the rotation of the Andromeda galaxy. He found that stars at the galaxy's outer edges were moving much faster than expected, suggesting far more mass than could be accounted for by visible stars. Initially, Babcock thought the unusual spinning might be caused by light absorption in the galaxy, or by differences in the outer regions, but his observations hinted at the presence of invisible matter. In 1940, Jan Oort made another key discovery. While studying the galaxy NGC 3115, he found a large, unseen halo of mass surrounding it, further suggesting that galaxies are filled with hidden matter beyond what telescopes can detect. The idea of dark matter really started to become popular in the 1970s. different scientific discoveries came together and suggested that galaxies might be surrounded by huge invisible halos of matter. In 1974, two separate research groups, one from Princeton, New Jersey, led by Jeremiah Ostraker, Jim Peebles, and Amos Yarheel, and another from Tartu, Estonia, led by Jani Nasto, Ensar, and Ants Kasik, reached the same conclusion on their own, which made the idea stronger. One important observation that hinted at these invisible galactic halos was how galaxies spin. Both regular light observations and radio astronomy played a big role in these findings. Vera Rubin and Kent Ford, using a new spectrograph, measured the speed of edge-on-spiral galaxies more accurately and found surprising results in how the galaxies rotated. At the same time, radio astronomers used advanced radio telescopes to study the 21-centimeter line of atomic hydrogen in nearby galaxies. Unlike starlight, which can only be seen from the inner parts of galaxies, hydrogen gas spreads much farther out. This let astronomers watch spinning patterns at much larger distances, giving a better idea of the total mass of a galaxy. Early studies of the Andromeda galaxy, using big telescopes like the 300-foot Green Bank telescope and the 250-foot Jodrell Bank dish, showed that the hydrogen spinning curve did not act as expected based on Kepler's laws, which explain how objects move around a centre of gravity. As technology improved, more sensitive equipment allowed even further measurements. In 1975, Roberts and Whitehurst pushed the limits, measuring the spinning speed of Andromeda all the way out to 30 kiloparsecs. They found that the galaxy's spinning curve stayed flat even at great distances. This was important because it suggested there was a lot more mass out there, beyond what we could see with normal telescopes. Their charts combined optical data from stars with the new hydrogen data, clearly showing the surprising flatness of the outer galaxy's spinning curve. The solid curve in the graph represented the optical data from stars, while the other curve showed the total mass, which kept increasing even in the outermost parts of the galaxy. At the same time, scientists were creating even better ways to study galaxies. Using interferometric arrays, several radio telescopes working together, researchers like Rogstad and Shostak in 1972 mapped the hydrogen spinning curves of 5 spiral galaxies. They found all these galaxies had flat spinning curves too, suggesting that the mass in the outer parts of galaxies was much higher than what could be explained by visible stars and light. By the late 1970s, most scientists accepted that dark matter halos probably existed around galaxies, making it one of the biggest mysteries in astronomy. In the 1980s and 1990s, many observations suggested that dark matter was real. One important study, done by Persic, Salucci and Stell in 1996, looked closely at 967 spiral galaxies and found strong evidence of dark matter. Other evidence included strange effects like gravitational lensing, where groups of galaxies bend light from objects behind them, the spread of hot gas in galaxies and galaxy groups, and the tiny temperature differences called anisotropies in the cosmic microwave background, the afterglow of the Big Bang. Today, most scientists agree that dark matter is made of particles that we have not yet discovered, and these particles are unlike anything we know. The search for this mysterious particle is now one of the biggest quests in particle physics, with many researchers using different methods and experiments to try to find it. Simply put, when scientists talk about matter in the universe, they mean anything that adds to the total energy, and its density changes in a certain way as the universe expands. Specifically, it decreases as the cube of the expansion, meaning the more the universe stretches, the thinner the matter becomes. This is different from radiation, which decreases even faster. Its energy gets weaker as the universe grows, following the inverse fourth power of the expansion. The cosmological constant, however, behaves differently. It stays the same no matter how much the universe stretches, so its energy density does not change. This difference in how matter, radiation, and the cosmological constant act comes from something called radiation redshift. If the observable universe doubles in size, the scale factor of expansion also doubles. As a result, the energy of things like the cosmic microwave background radiation, the afterglow from the Big Bang, becomes weaker because each photon, light particle, has to stretch over a larger space. The same happens to very fast-moving particles like early neutrinos. They lose energy in a similar way. But the cosmological constant being a property of space itself does not change no matter how much the universe grows. Dark matter generally refers to parts of the universe we cannot see, but that still have mass and follow similar rules as regular matter. More specifically, it often describes a special kind of invisible matter that is not made of the normal particles we know, excluding something called missing baryons. Depending on the context, the meaning of dark matter can change. The arms of spiral galaxies spin around their centers, and as you move outward, the visible mass density of the galaxy decreases. If all the galaxy's mass were visible, it would act like a simple system with most mass at the center and objects orbiting around it, like planets orbiting the Sun. Based on Kepler's third law, we would expect objects to move slower the further they are from the center, just like planets move slower the further they are from the Sun. But this is not what we see in galaxies. Instead, stars and gas in galaxies keep moving at roughly the same speed, or even faster, the farther they are from the center. To explain this, it seems clear that the mass in spiral galaxies is spread out differently than in the solar system. There may be a large amount of invisible non-light emitting matter, what we call dark matter, at the edges of galaxies. In systems like galaxies, stars are also affected by a rule called the virial theorem, which helps explain how mass is spread out based on the speeds of stars. When astronomers measure the speed of stars in systems like elliptical galaxies or dense star clusters, they can use this rule to figure out how mass is distributed. Often, the measured speeds do not match what we would expect based on the visible mass, even when considering the complex movements of stars. Like the spinning curves of galaxies, the most likely explanation for this mismatch is that there is more invisible matter. Again, dark matter. Galaxy clusters are important for studying dark matter because we can measure their mass in three ways: by looking at the range of speeds at which galaxies in the cluster move, by studying X-rays from the hot gas inside the cluster. By analysing the X-rays, scientists can determine the gas's temperature and density, which allows them to calculate the pressure. Using the balance between gravity and pressure, they can estimate the total mass of the cluster. Through gravitational lensing, where the cluster's mass bends light from more distant objects. This lets scientists measure the cluster's mass without watching the galaxies move. All three methods point to the same conclusion. Dark matter makes up roughly 5 times the mass of all visible matter in these clusters. One interesting result of Einstein's general relativity is gravitational lensing. This happens when big objects like galaxies or galaxy groups sit between a light source and the observer. These objects act like a lens, bending the light, making the source look different. Importantly, gravitational lensing only needs mass. It does not matter what the mass is made of. The more mass an object has, the more it bends light. For example, if a group of galaxies lies between a very far away object like a quasar and us, the galaxies bend the quasar's light, making it look changed. Strong lensing refers to dramatic bending of light, creating arc shapes as it passes through a big object's gravity. This has been seen around many distant galaxy groups, including one called Abell 1689. By studying the arcs, scientists can figure out the mass of the galaxy group causing the bending. Weak lensing is less noticeable. Galaxies do not turn into arcs but show tiny distortions. Studying these small changes tells scientists how dark matter is spread in the universe. The patterns of mass and light match what we expect from dark matter studies. Although dark matter and normal matter are both forms of matter, they behave differently. Early in the universe, normal matter was charged and interacted strongly with light, causing it to scatter. Dark matter does not interact directly with light, but still affects the universe. For example, it influences the cosmic microwave background, CMB, through gravity, especially on large scales. It also affects how normal matter moves and is spread out. Because of this, normal and dark matter evolve differently and leave separate traces on the CMB. The CMB is almost a perfect blackbody, meaning it has an even temperature. But there are tiny differences, about 1 part in 100,000, that scientists can study. These small differences, called anisotropies, can be mapped across the sky. When scientists turn this map into a graph called the angular power spectrum, they see peaks that are evenly spaced but have different heights. The positions of these peaks depend on important factors in cosmology. By comparing them with theoretical models, scientists can learn more about the makeup of the universe. The first discovery of the unevenness in the cosmic microwave background, CMB, came in 1992 by the COBE satellite, but the images were not clear enough to see the detailed peaks. In 2000, the Boomerang experiment, which used a balloon to take measurements, found the first of these peaks. Later, the WMAP satellite and the Planck spacecraft measured these peaks much more accurately. Their findings supported the lambda CDM model of the universe. Structure formation is the process that began shortly after the Big Bang, when small differences in the universe's density caused matter to collapse and form stars, galaxies, and clusters of galaxies. Before this time, the universe was smooth and even, with no major differences in density, as described by the Friedmann solutions to general relativity. Over time, tiny differences in density began to grow and come together, turning the smooth, featureless universe into a more complex one filled with stars and galaxies. In the early stages, radiation was the main form of energy in the universe and had a big effect on matter. This radiation stopped normal matter from clumping together and forming structures. If the universe only had normal matter, these differences would not have had enough time to grow into the galaxies and clusters we see today. The key to solving this problem is dark matter, which is not affected by radiation. This allowed its density changes to grow first, creating gravity wells that later helped normal matter collapse into galaxies and other structures. The pull of gravity from dark matter acted like a magnet, pulling in normal matter and speeding up the formation of these large cosmic structures. A striking example of dark matter's effect is the bullet cluster, formed when two large galaxy clusters collided. What makes the bullet cluster especially interesting is the difference between where the mass is located according to the bending of light by gravity and where the visible matter is. This difference is hard to explain with other gravity theories, which expect the bending of light to happen only around visible matter. But the standard dark matter theory explains it easily. The visible gas in the clusters, which interacts with light and radiation, was slowed down and cooled by electromagnetic forces during the collision. Dark matter, on the other hand, doesn't interact with light in the same way, so it passed through the collision without being affected, separating from the visible gas. This created two separate peaks in the bending of light, as observed. In addition to dark matter, astronomers use type Ia supernovae as standard candles to measure distances across the universe. These supernovae have a known brightness, so by measuring how dim they appear, scientists can calculate how far away they are. This method has shown that the universe is expanding faster and faster, a phenomenon usually explained by dark energy. Baryon acoustic oscillations, BAO, are regular changes in the density of normal matter, baryons, in the universe, which happened on large scales in the early universe. These changes were caused by sound waves moving through the hot, dense mix of photons and baryons before the universe cooled enough for atoms to form. The effects of these sound waves can still be seen in the cosmic microwave background. As the universe expanded, dark matter and normal matter began to come together, but the effect of the original changes became weaker over time. However, we can still see a small preference for galaxies to be separated by about 147 million light-years, which is a subtle but measurable sign of these early changes. This pattern was predicted in the 1990s and confirmed in 2005 through large galaxy surveys like the Sloan Digital Sky Survey and the 2-degree Field Galaxy Redshift Survey. By combining CMB observations with BAO measurements, scientists can get a precise estimate of important cosmic values, such as the rate of expansion of the universe and the amount of matter it contains. These results support the lambda CDM model, which is the current leading theory of the universe. Large surveys of galaxy redshifts help us create a three-dimensional map of how galaxies are spread out in space, but these maps are not perfect because the distances we estimate are based on the redshift we see. The redshift we measure is affected by two things. The main factor is the universe's expansion, but there is also a smaller effect from the galaxy's own motion, called its peculiar velocity. In general, superclusters, groups of many galaxies, grow more slowly than the average expansion of the universe because their gravity pulls things together. On the other hand, voids, huge empty spaces between galaxies, expand faster than the universe as a whole. This difference in expansion causes some interesting effects. For example, galaxies in front of a supercluster move toward it faster than expected, so their redshift will be a little higher than we would normally calculate. Conversely, galaxies behind the supercluster appear to have a slightly lower redshift than expected. This difference makes superclusters look flattened along our line of sight, while voids look stretched. However, this effect is hard to notice in a single structure, since we don't know its exact shape. Instead, scientists can see this effect by averaging data from many structures. This phenomenon was first predicted by Nick Kaiser in 1987 and later confirmed in 2001 by the 2-degree field galaxy redshift survey, with results matching what we expect from the lambda CDM model. In a related field, the Lyman alpha forest is the collection of absorption lines seen in the light from distant galaxies and quasars. These lines are caused by neutral hydrogen absorbing light at a specific wavelength called the Lyman alpha transition. Observations of the Lyman alpha forest help astronomers test and improve models of the universe, with results that agree with findings from WMAP. Dark matter is often divided into 3 types: cold, warm, and hot. These names don't mean temperature, but instead describe how fast the particles were moving in the early universe. In simple terms, they show how far the particles travelled due to random movements before the universe started expanding and slowing them down. This distance is called the free streaming length, FSL. The type of dark matter depends on how this FSL compares to the size of a protogalaxy, an early cosmic object that would later become a small galaxy. If the FSL is much smaller than the protogalaxy, it's called cold dark matter. If it's about the same size, it's warm dark matter. If the FSL is much larger, it's hot dark matter. Some theories suggest a mix of these types, which were more popular in the middle of the 1990s, but became less favoured after the discovery of dark energy. The main idea behind the free streaming length is that, after the Big Bang, the universe started with small changes in density caused by tiny quantum fluctuations at the smallest scales. As these particles move from denser areas to less dense ones, the fast expansion of the universe limited how far they could go. Faster particles, like those in hot dark matter, could travel farther before the universe expanded too much, while slower particles, like those in cold dark matter, couldn't move as far. This means that the free streaming length sets a limit on the size of structures that could form in the early universe. Hot dark matter would form large structures, like superclusters, which would later break apart into galaxies. Cold dark matter allows smaller structures, like galaxies, to form first. Recent observations, especially deep field images of the universe, show that galaxies formed first, followed by clusters and superclusters as galaxies grouped together. This supports the idea that most dark matter is cold, not hot. This is also why neutrinos, which move almost at the speed of light and would be considered hot dark matter, cannot explain most dark matter. Dark matter refers to any kind of matter that interacts with visible matter, like stars and planets, mainly through gravity. This means that dark matter might not be a completely new type of particle, but could, in theory, include normal matter like protons or neutrons. In fact, many objects familiar to astronomers, such as planets, brown dwarfs, red dwarfs, stars, white dwarfs, neutron stars, and black holes, fall into this category. For example, when a black hole pulls in matter, it doesn't care whether it is normal matter, like protons or other kinds of matter. Once it's inside the event horizon, all matter is treated the same. These hard-to-see objects are grouped together as machos, massive compact halo objects. Some scientists once thought machos made up most dark matter, but this idea has mostly been rejected. There is strong evidence that most dark matter is not made of normal visible matter. First, if there were enough normal matter like gas or dust, we would be able to see it when it is lit up by stars. But we don't see this kind of matter in the amounts we would expect. Next, the Big Bang theory helps us understand how the elements we see today were formed. According to this theory, if there had been more normal matter, called baryons, in the early universe, we would see a higher amount of elements like helium, lithium, and other heavier elements. Based on what we observe, we know that only about 4 to 5% of the universe's total mass is normal matter. However, large-scale studies of galaxies and other cosmic structures show that the total amount of matter is about 30% of what is needed to keep the universe stable. Further studies have shown that only a small part of dark matter seems to be normal. Hidden objects, like small planets or black holes, called machos. Studies involving the bending of light by gravity suggest that these objects cannot make up most dark matter, as their masses exclude almost all possible candidates. Detailed studies of the cosmic microwave background, the faint radiation left from the Big Bang, by missions like WMAP and Planck, provide strong evidence that about 5/6 of the matter in the universe does not interact much with light or normal matter, except through gravity. This suggests that dark matter is mostly invisible and can only be detected by its gravitational pull. If the ordinary matter we know, called baryonic matter, does not make up most of dark matter, then dark matter must be something different, called non-baryonic matter. There are two main ideas for what this non-baryonic matter could be: unknown, mysterious particles, or very old black holes that formed in the early universe. Unlike ordinary matter, these unusual particles do not help make the elements formed during the Big Bang. We only notice them because of their effects on gravity, such as how they bend light, a phenomenon called weak lensing. Some types of dark matter can even interact with themselves or with normal particles, like WIMPs, which are weakly interacting massive particles. These interactions might produce signals like gamma rays or neutrinos, which scientists might be able to detect. There are many possible types of dark matter, each with advantages and challenges. WIMPs are thought of as tiny particles that mostly interact through gravity, and perhaps some weak forces, like the weak nuclear force. Many theories suggest that WIMPs were made in the early universe, similar to ordinary particles. These WIMPs would form what is called cold dark matter. To match the amount of dark matter we see today, WIMPs would need to be able to destroy each other in a certain way. This matches what would happen if their mass were around 100 billion electron volts and they interacted through the electroweak force. This idea is often called the WIMP miracle because it fits so well with predictions from supersymmetry, a theory that extends the standard model of particle physics. A stable particle predicted by supersymmetry has long been seen as a prime candidate for dark matter. Scientists have been trying hard to find WIMPs. They look for signs of WIMPs destroying each other, such as gamma rays, neutrinos, and cosmic rays coming from nearby galaxies. They also try to detect WIMPs directly in laboratories by observing how they interact with atomic nuclei, or by creating them in particle colliders like the Large Hadron Collider. However, in the early 2010s, experiments did not find strong evidence for supersymmetry, and the results from the Large Hadron Collider made simple WIMP ideas seem less likely. Axions are another type of dark matter particle. They were first suggested in 1978 by Frank Wilczek and Steven Weinberg to solve a problem in the theory of quantum chromodynamics, which explains how quarks and gluons interact. Axions are extremely light and weakly interacting, making them a good candidate for dark matter. They could have formed in the early universe and still exist today, with the number of axions depending on their mass. Axions might also explain some of the smaller scale mysteries in our leading cosmological model, lambda CDM. Interest in axions has grown in recent years, especially because WIMPs have not been detected. Their tiny mass means quantum effects might help explain some of the strange behaviours of dark matter. Primordial black holes are another fascinating idea. They may have formed just after the Big Bang, during a time of rapid expansion called inflation. Extremely dense regions of subatomic matter could have collapsed under their own gravity, forming black holes without the death of stars, which is how regular black holes form. These primordial black holes would have existed before the first stars and could have masses from as small as atoms to much larger than typical stellar black holes. The idea of primordial black holes was first suggested in 1967 by Yakov Zeldovich and Igor Novikov, and later by Stephen Hawking in 1971. It quickly became a possible explanation for dark matter. One advantage of this idea is that black holes are already well understood in physics through general relativity, and we already know black holes exist. However, creating primordial black holes might need special conditions, like unusual types of cosmic inflation or physics beyond the standard model. In 2015, the detection of gravitational waves from merging black holes renewed interest in primordial black holes as dark matter. Some of these black holes were more massive than expected from normal stellar collapse, suggesting they might be primordial. But a study searching for gravitational lensing effects from medium-sized black holes found no evidence for them, although this could depend on assumptions about their mass. Future observations, such as those from the James Webb Space Telescope, may give more answers. Some scientists thought tiny primordial black holes could make up much of dark matter. However, the Voyager 1 spacecraft measured the flow of positrons and electrons beyond the Sun's influence and found fewer particles than expected, with the wrong energies. This suggested that these tiny black holes are too rare to explain dark matter. Despite this, the idea of dense forms of dark matter is still being studied. Some new theories even propose ways to cool dark matter. As of 2018, the mystery remains unsolved. In 2019, observations of the Andromeda galaxy showed no signs of microlensing, which would appear if tiny black holes were there, adding more doubt. Yet there is still a range of masses too small to detect with current methods, where primordial black holes could still make up dark matter. If dark matter is made of particles that barely interact with anything, a key question arises. Could these particles form objects like stars, planets, or black holes? So far, the answer is no, and there are two main reasons. First, dark matter cannot easily lose energy. Ordinary matter forms dense objects because it can release energy as particles fall inward due to gravity. Dark matter cannot do this, so particles that start to collapse just heat up, speed up, and escape, preventing dense objects from forming. Second, dark matter does not interact in many ways. Ordinary matter interacts through gravity, electromagnetism, and the strong nuclear force, allowing complex structures like atoms and stars. Dark matter only interacts weakly, if at all, so it cannot form such structures. If dark matter is made of subatomic particles, they pass through every square centimetre of Earth millions or billions of times every second. Many experiments are trying to detect this. WIMPs have been the main focus, but axions are also being studied, for example in the axion dark matter experiment. Other possibilities include heavy particles that interact only through gravity. There are two main ways to study dark matter. Direct detection experiments look for particles scattering off atomic nuclei. Tiny amounts of energy are released, which can be measured as light or vibrations. These experiments are usually deep underground to avoid interference from cosmic rays. Some of the main laboratories are Storwell Mine, Sudan Mine, and Gran Sasso. Experiments use technologies such as cryogenic detectors that measure heat and Nobel liquid detectors that measure light, with famous examples being CDMS, CREST, Xenon, and ELUX. Indirect detection experiments search for dark matter particles destroying each other or breaking down. So far, no confirmed detection exists, but these searches help narrow down possible properties. The DAMA and DAMA Libra experiments observed yearly changes in data that might be due to the Earth moving through a dark matter cloud. Other experiments, like LUX and Super CDMs, have not seen the same effect. Some experiments also track the direction of dark matter based on the solar system's motion, trying to distinguish dark matter signals from background noise. Dark matter particles can collide in space, especially in areas with high dark matter, such as the centre of the Milky Way. These collisions could release gamma rays or particle-antiparticle pairs. Unstable dark matter particles might break down and produce gamma rays, antiprotons or positrons. Detecting these signals is tricky because other cosmic events can produce similar effects. Dark matter passing through the Sun or Earth could collect at their centres, increasing the chance of collisions that emit high-energy neutrinos. Instruments like Amanda, IceCube, and Antares are searching for this. Gravitational wave detection by LIGO in 2015 also opened new ways to study dark matter if it exists as primordial black holes. Some experiments have looked for emissions from dark matter. For example, in 2008, the Energetic Gamma Ray Experiment Telescope saw more gamma rays than expected, though this may have been a measurement error. The Fermi Gamma Ray Space Telescope continued this search and in 2009 observed extra gamma rays from the Milky Way centre. In 2012, Fermi data analysis suggested a signal at 130 billion electron volts, possibly from WIMP destruction. Ground-based telescopes also searched for signals in dwarf galaxies and galaxy groups. The Pamela experiment, launched in 2006, detected an unusual number of positrons, possibly from dark matter or pulsars, while the Alpha Magnetic Spectrometer on the International Space Station observed high-energy cosmic rays in 2013, possibly linked to dark matter. Another approach is to create dark matter in laboratories. The Large Hadron Collider may produce dark matter in proton collisions. Because dark matter hardly interacts with normal matter, it might be detected indirectly by missing energy, while other particles are measured. Similar tests, like the LEP experiment, studied interactions between dark matter and electrons. Any discovery must be confirmed through other direct or indirect detection methods to prove it is really dark matter. Since dark matter has not yet been identified, alternative theories exist. General relativity works well in the solar system, but is less tested on galactic scales. Some scientists suggest modifying general relativity could remove the need for dark matter. Examples include Mond, modified Newtonian dynamics, TeVs, FR, gravity, negative mass, dark fluid, and entropic gravity. The challenge for these alternatives is that evidence for dark matter comes from many independent sources. Explaining all observations without dark matter is very difficult. Some alternatives have shown limited success, such as a 2016 test of gravitational lensing in entropic gravity, and a 2020 study supporting Mond. Still, most astrophysicists believe that while changes to general relativity may explain some observations, the overall data strongly suggests that dark matter exists in some form. In the decade of the 1990s, two independent teams of astronomers set out on a bold mission. One team was led by Saul Perlmutter, while the other was headed by Brian Schmidt and Adam Rees. Their focus was on a special kind of exploding star called a Type Ia supernova. These supernovas are astonishingly bright, outshining entire galaxies for a brief time, and they all explode in almost the same way. That makes them excellent cosmic mile markers. If you know how bright a Type Ia supernova should be, and it appears dimmer, you know it lies farther away. The scientists' goal was to measure how quickly the expansion of the universe was slowing down. Yes, slowing down, because at that time, most people assumed the universe behaved like a ball thrown into the air. After the Big Bang sent everything flying outward, gravity, the great cosmic pull, should have been slowing that expansion, perhaps even preparing to pull everything back together in the distant future. But the data told a very different story. When the teams measured the supernovas, the results simply did not add up. The galaxies were not just far away, they were too far away. Their light was more redshifted than expected, meaning they were racing away faster than they should have been. The universe was not slowing down, it was speeding up. Now imagine being a physicist at that moment, in the year 1998, suddenly realizing that everything you thought you knew about the universe's destiny was wrong. The researchers checked and rechecked their work, but every test confirmed the same shocking truth. Some invisible force was pushing the universe apart faster and faster, with no sign of stopping. They named this strange and unseen influence dark energy. What is dark energy made of? We still have no idea. We do not even know if it is a thing at all. But we do know that it is real, because its effects are written across the heavens. Even more unsettling, dark energy is not just a small piece of the cosmos, it dominates it. Roughly 70% of everything in existence, every particle, every wave, every scrap of energy and matter is dark energy. Think about how strange that is. Everything you have ever known, everything you have ever seen or touched or heard, every planet, every star, every atom, makes up less than 5% of the universe. About 1/4, 25%, is dark matter, an invisible substance that binds galaxies together with its gravity. But the largest portion, the majority slice of the cosmic pie, belongs to this silent, unseen force that stretches space itself apart. So what could dark energy actually be? That is where the puzzle deepens. The simplest guess is that dark energy is just the natural energy of empty space, often called vacuum energy. For even when space appears to be empty, quantum physics tells us it is not truly empty. It is filled with restless fluctuations, tiny bursts of energy that flicker in and out of existence. Here is where the mystery grows almost absurd. When physicists use quantum theory to calculate how much energy should exist in empty space, the result is staggering. The equations predict a value that is one followed by 120 zeros, times greater than what we actually observe. In other words, the theory overshoots reality by the single largest mismatch between prediction and observation in the entire history of science. It is as if you tried to weigh a feather and your calculator insisted that it was heavier than the entire Earth. Clearly something is very, very wrong. Yet according to Einstein's equations, energy, any energy at all, warps the fabric of space-time. That means if space has this vacuum energy built into it, it must directly affect the way the universe expands. And since we see the expansion accelerating, perhaps this vacuum energy is the very thing driving the cosmic push we call dark energy. But if that is the case, then why is the number so catastrophically off? Either our theories are missing something vast and essential, or we're staring at a piece of the puzzle we still cannot fit into place. To make sense of it, picture space as a giant loaf of raisin bread. The raisins are galaxies baked into the dough. As the bread rises, the raisins drift apart from each other. That is the universe expanding. Now, imagine that halfway through baking, the oven's heat is suddenly turned up far higher. The dough does not just rise gently anymore, it balloons outward at a furious pace. That sudden extra push is what dark energy does to the universe. The most unsettling part is that dark energy does not thin out as the universe grows. The more space there is, the more dark energy exists, which means it can never run out. It is baked into the very structure of the cosmos. And so, here we stand, in a universe that is not just expanding, but expanding faster and faster. The hidden engine behind this runaway growth is dark energy, this invisible, untouchable force that cannot clump, cannot be slowed, and grows stronger the more room it is given. That is already strange enough. But then comes the haunting question: where does this lead us? If dark energy keeps pushing forever, what becomes of the universe in the end? One possible answer is among the most terrifying predictions ever made in cosmology. Scientists call it the Big Rip. Right now, gravity still rules the neighborhoods of the cosmos. On the scale of galaxies and solar systems, it holds things tight. Galaxies stay whole, stars orbit their centers, and planets cling to their suns. Space itself is stretching, but inside a galaxy the pull of gravity wins over that stretching, at least for now. Dark energy, however, plays by its own rules. It does not stay still. It can grow stronger and push harder. In some ideas, it doesn't merely make the universe expand faster, it makes the speed of that expansion itself speed up. Think of sitting in a car that keeps picking up speed as it goes downhill, and then the hill suddenly gets steeper. That is the picture behind the Big Rip. At first the ripping would be subtle. Galaxy clusters would drift apart. Nearest neighbours that once might have met would be pulled away forever. The space between our Milky Way and the Andromeda galaxy would stretch so fast they could never collide. Later the violence would reach inside galaxies themselves. They would begin to pull apart, not gently but by tearing. Gravity would grow too weak to hold stars in their orbits. Whole star systems, planets, moons, rings, would come undone. Planets could be flung off on wild paths, moons would slip away into empty space, and the tides that once kept things steady would vanish. If the acceleration kept strengthening, even the Earth would not escape. The stretching could overwhelm the electromagnetic forces that hold molecules and solids together. Crusts would fracture, molecules would separate, atoms could be pulled apart, and in extreme models even protons might be torn as space stretches beyond what particles can withstand. In the final moments before a full Big Rip, the universe would be a storm of broken pieces and scattered particles. No atoms, no stars, no galaxies, only unbound energy and empty space. In one rough estimate based on a particular model, that end could come in about 22 billion years. But that number is only a guess for one model. It could come sooner, or it might never happen at all, depending on how dark energy actually behaves. Not every story ends in shredding. There is another possibility that asks a different question. What if the expansion does not go on forever? What if at some time gravity fights back? Early on, the universe was hot and dense, and the two forces, expansion and gravity, pulled against each other. For a long time, many scientists imagined that gravity might one day win that tug of war. In the Big Crunch version, dark energy fades or was never permanent, and gravity slowly reasserts itself. Expansion would stop and reverse. Galaxies that once drifted apart would draw together again. The great cosmic web, the filaments of galaxies and voids, would contract. Over huge stretches of time, the universe would shrink. Temperatures would climb as everything was squeezed into less space, and the night sky would grow brighter as stars and galaxies collided and blended together. Space-time itself would fold inward like a closing fist. in the last instance the entire cosmos might collapse into a single hot, dense point, an end that mirrors the beginning. There is something almost poetic about that symmetry, the universe ending where it began. But the crunch has a problem. Observations so far, the redshifts of distant galaxies and the detailed pattern of the cosmic microwave background, tell us the universe is not slowing down, it is speeding up. Right now, gravity does not appear to be winning, so unless dark energy changes dramatically in the future, a big crunch looks unlikely. That leads to a quieter, lonelier possibility, the big freeze. This ending is not violent. It is a long, slow fading into cold and darkness. Many cosmologists favour it because our best current measurements, for example from the Planck satellite, and large surveys like the Sloan Digital Sky Survey, fit a simple form of dark energy called a cosmological constant, which stays roughly the same over time. If that picture holds, the universe will keep stretching and stretching. Galaxies will drift ever farther from one another. Over the course of time, the part of the universe we can see, our observable universe, will shrink in the sense that distant galaxies slip beyond our cosmic horizon and vanish from view, like ships slowly sailing over the edge of an endless ocean. Give it about 100 billion years and the sky we can observe will be dramatically emptier. After more time, even the nearest galaxies will be gone from sight. The Milky Way and Andromeda, which long ago will have merged into a single giant elliptical galaxy, will become an island alone in an ever darker sea. Star formation will not last forever. Stars need cold hydrogen gas to be born, and that fuel runs out. As time goes on, galaxies recycle less material into new stars. The supply is used up. Estimates put the end of significant star formation at around 1 trillion years from now. After that, the remaining stars will slowly burn out. The universe will not explode or snap shut. It will cool and fade. Black holes will win over long stretches of time, but will themselves evaporate very slowly. The end, in this view, is not a dramatic finale, but an endless silent wind down. A cosmos that dies of cold and isolation rather than flame or collapse. Which of these futures is correct, rip, crunch, or freeze, depends on the true nature of dark energy. Right now, dark energy is a name for something we can measure but still cannot explain. If someone cracks what it really is, it would change everything we think about the universe, and almost certainly be a discovery worthy of the highest honours in science. Until then, we write these endings as stories built from the hints we see, some dramatic, some gentle, all depending on the one thing we have yet to understand. Red dwarfs are the small, faint and cool stars of the cosmos. They are not as dazzling as suns like ours, yet they are the champions of endurance. While massive stars burn bright and die young, red dwarfs can survive for trillions of years, far, far longer than the current age of the universe itself. In the distant future, when most other stars have already faded, these tiny red beacons will be the last lights glittering in the endless night. But even red dwarfs cannot shine forever. Their fuel will eventually run out, and one by one, they too will die. What will remain then are only the cosmic leftovers. The dense white dwarfs that were once stars like our Sun, the ultra-heavy neutron stars born from violent supernovae, and the mysterious black holes that devour everything unlucky enough to wander too close. This is the beginning of what scientists call the Degenerate era, a time when no new stars are born, no new light is made. The universe will be filled with the ashes of creation, dim brown dwarfs, silent white dwarfs cooling into darkness, and black holes that still hunger, still consuming matter in the silence of eternity. But time does not stop. It marches forward, endlessly. Over the course of 10 to the power of 40 years, that is, a 1 followed by 40 zeros, the universe's stellar corpses will continue to decay. White dwarfs will radiate away their last warmth until they become frozen, invisible black dwarfs. Neutron stars, so dense that a teaspoon of their matter outweighs a mountain, may persist for unimaginable stretches of time. But even black holes, which seem so eternal, carry their own secret expiration date. Physicist Stephen Hawking discovered that black holes are not completely permanent. Through a subtle quantum effect now known as Hawking radiation, they very slowly lose mass. A black hole the size of our Sun would take about 10 to the power of 67 years, a 1 followed by 67 zeros, to finally vanish into nothing. Compare that to the age of our universe today, only about 13.8 billion years, and you begin to see the absurd scale of these numbers. Our present age is just the opening flicker of the story, barely the first breath in an eternity. In what scientists call the Big Freeze, time stretches on to horizons beyond human imagination. Black holes shrink, evaporate, and disappear one after another, each ending with a faint whisper of radiation. Then there are no more stars, no more planets, no more sources of light. The universe becomes a ghostly sea filled only with scattered particles, lonely electrons, positrons, and perhaps protons, drifting endlessly in the cold. The temperature of space plummets toward absolute zero, not because heat has been turned off, but because there is nothing left to produce it. No nuclear fusion, no gravitational collapse, no fiery stars to keep the cosmos warm. Just an expanding void, a silent ocean of darkness where particles are so far apart they can never touch. And even the protons, the building blocks of atoms, may not be eternal. Some theories suggest that after about 10 to the power of 36 years, protons themselves might decay. If this is true, then every last trace of matter, every atom, every molecule, every remnant of planets and stars will crumble away until nothing tangible remains. What would be left after that? Almost nothing at all. Only a fading background glow of radiation, the last echo of a universe that once blazed with stars, galaxies, and perhaps life. The cosmos will continue expanding, but with nothing left to change, nothing left to create, and no one left to witness. Even the very idea of place will lose its meaning, for without matter, there will be nothing to mark here or there. The laws of physics, the rules that gave birth to galaxies, suns, and living beings, will still exist, etched into the frozen fabric of space-time. But there will be no one left to read them, no one to marvel at what once was. And that will be the final fate of our universe, a silent, endless, and empty void. The question of how the universe will end is one of the most fascinating mysteries in all of science. Over the years, scientists have suggested several different ideas about the final fate of everything. All of these ideas depend on one key thing: the expansion of space itself. This expansion is like an invisible force that stretches the universe wider and wider over time. The future of the universe, whether it keeps expanding forever, stops expanding, or even reverses its course, depends on how this stretching of space behaves in the long run, and that in turn affects what happens to matter, energy, and all the basic forces that shape the universe. Besides the well-known endings called the Big Freeze and the Big Rip, there is another dramatic possibility that scientists have imagined, the Big Crunch. This idea suggests that the expansion of the universe might not continue forever. If there is enough matter and energy spread throughout space, gravity, the force that pulls things together, might eventually become strong enough to stop the expansion completely. And if that happens, the universe would start to shrink instead of grow. In this Big Crunch picture, galaxies would begin moving closer together, stars would fall inward, and planets, including our own, would slowly be pulled toward one another. Over an extremely long stretch of time, all of this matter would collapse into a single, unbelievably dense point, possibly ending in something like the Big Bang, but in reverse. It would be as if someone rewound the entire universe back to its very beginning. However, the Big Crunch is not the most popular idea right now. Observations made by astronomers in the past few decades suggest that the universe's expansion is actually speeding up, not slowing down. That means the Big Crunch seems unlikely, at least for now. But scientists say it could still be possible if something about the mysterious force called dark energy were to change in the future. There is another, even stranger possibility that comes from the world of quantum physics. This idea is called vacuum decay. According to this idea, the universe might not be in its most stable form at the moment. Instead, it could be resting in a kind of false or temporary vacuum, a fragile state of space that looks stable but is not truly permanent. One day, by pure chance, a tiny bubble of true vacuum might suddenly appear because of a random quantum event. This bubble would spread at the speed of light, destroying everything in its way. Whole galaxies, stars, planets, and even atoms would vanish as the bubble changed the universe into something completely different. And because this could happen at any moment, without any warning, we might never see it coming. Beyond these ideas lies a whole set of possibilities that are even more uncertain. Ideas about the multiverse, which is the thought that our universe is just one among many. In some versions of this idea, black holes could act like tunnels or doorways to other universes. So as our universe reaches its end, maybe new ones are being born elsewhere. In this view, while our own universe may one day die, the multiverse itself could go on forever, cycling through endless births and deaths. Now let us explore something that sparks the imagination even more. Could life survive in a universe that is slowly freezing and growing dark? Most scientists believe the universe's most likely ending is a slow and quiet one, a future called the heat death, or the big freeze. In this version of the end, stars burn out one after another, galaxies drift farther and farther apart, and in time, everything becomes dark, empty, and unimaginably cold. Temperatures would fall so close to absolute zero, the coldest temperature possible, that hardly any energy would remain to power anything at all. At first, this seems like a hopeless future for life. After all, life as we know it depends almost completely on stars. On Earth, for example, sunlight powers nearly every ecosystem. The heat and light from our sun are what make the planet warm enough for living things to survive. But in a universe without stars, what could possibly keep life alive? Surprisingly, there are some chances. If intelligent civilizations exist and if they are advanced enough, they might find new ways to survive without starlight. For example, they might gather energy from black holes, which last long after stars have died. Some scientists believe that as matter falls into a black hole, it gives off huge amounts of energy. Advanced beings might be able to capture this energy and use it to power their civilizations. Another idea is that life could slowly adjust to the harsh conditions of a cold, dim universe. On Earth, we already see examples of life thriving in extreme places. These are called extremophils, tiny organisms that live in boiling hot springs, deep ocean vents, freezing Arctic waters, or even highly radioactive areas. If life can survive in such tough places here, maybe, given enough time, it could change and survive in the frozen universe of the far future. In that faraway time, life might look nothing like what we see today. It could function using very different chemical processes, needing only tiny amounts of energy to stay alive. Or maybe intelligent life would use technology to build artificial worlds, places where heat and light could be saved, reused, and carefully controlled. Civilizations might build enormous machines to catch and store the last scraps of energy left in the universe. They could also find ways to slow down their life processes, the chemical reactions that keep living things alive, so they need far less energy to keep going. In this kind of future, time itself could become the most valuable resource. Survival might depend on stretching the remaining energy over billions or even trillions of years. And maybe, just maybe, if life becomes advanced enough, it could learn to control the very fabric of the universe. This might include using dark energy itself, bending space and time, or unlocking new powers from strange quantum fields. These ideas sound like science fiction today, but they show the amazing creativity and adaptability that intelligent life might develop when faced with the greatest challenge of all: how to go on in a universe that is slowly dying. Still, even with all these fascinating ideas, there may be a limit to how long life can last. In a universe that keeps expanding forever and grows colder and darker with each passing age, there may come a time when not even the most advanced technology or the toughest life forms can continue. And yet, the story of the universe's end is far from finished, because with every new discovery, science finds new possibilities. As the universe keeps stretching and expanding over time, the spaces between galaxies grow wider and wider. This means that any civilization still out there would slowly become more and more cut off from one another. At first, it might just be harder to send messages or travel between galaxies. But in the end, as the galaxies keep drifting apart faster and faster, faster even than the speed of light, communication and travel would no longer be possible at all. Each civilization would end up trapped in its own small patch of space, like a tiny island in a huge and growing cosmic ocean. This kind of isolation would be impossible to avoid because of the unstoppable expansion of space itself. As the universe heads toward what scientists call heat death, things take an even darker turn. In that distant future, which might happen trillions upon trillions of years from now, everything would slow down. The temperature everywhere would drop closer and closer to absolute zero, the coldest temperature nature allows. At this point, even the most basic processes, like chemical reactions and the movement of atoms, would begin to freeze and stop. Life, no matter how smart or advanced, needs energy to survive. But in a nearly frozen universe with almost no energy left, even the most energy-saving forms of life would struggle to go on. Simple things like thinking, reproducing, or keeping a body working would become too hard. Eventually, the energy needed just to stay alive might be impossible to find. Still, some scientists and thinkers have dreamed up amazing possibilities. What if, far in the future, life could take on a form that does not depend on energy the way we know it? Maybe life would not need to be made of carbon or other familiar elements. It might not even need a physical body at all. In one astonishing idea, life could become purely informational. That means it could exist as patterns of data or awareness stored in some kind of digital or quantum system. In this form, life might continue long after the universe has become too cold for anything biological to survive. These life forms might not need matter, and they might not age or decay in the usual way. If such a transformation is possible, life could last almost forever, even as the universe itself is dying. Some even bolder ideas suggest that life might find a way to leave this universe altogether. According to the theory of the multiverse, our universe may be just one of many. Other universes might have different rules, different types of matter, or even better conditions for life. If an extremely advanced civilization learned how to move from one universe to another, they might escape this dying cosmos entirely, finding safety in a new universe full of possibilities. But even before the universe reaches its cold and quiet end, one of the first signs of deep change would be the collapse of communication between galaxies. Right now, galaxies are still close enough, at least on a cosmic scale, that they can be seen with powerful telescopes. But as space continues to stretch faster and faster, they will drift so far away that they will no longer be visible, even with the best tools. They will fade beyond what scientists call the observable horizon, meaning they will disappear from sight forever. Not only will we no longer be able to see them, but we also will not be able to send or receive any signals from them. Whether we use radio waves, light signals, or even the most advanced communication methods we can imagine, none of them would reach other galaxies once they are too far away. No signal can move faster than light, and the expansion of space itself would outpace even the fastest signals. This growing silence would have a deep impact. If other intelligent life exists in faraway galaxies, then the early days of the universe may have given a short window of time when communication was possible. Even though we have no proof that this ever happened, the chance of intergalactic contact would vanish completely as the universe keeps expanding. In the far future, each galaxy, or more exactly each cluster of galaxies held together by gravity, will become its own self-contained cosmic island. There will be no way to cross the vast emptiness between these islands. The rest of the universe will become dark, silent, and unreachable. This extreme isolation will not only stop communication, it would also end the sharing of knowledge, discoveries, and perhaps even resources. If advanced civilizations once traded or shared science across galaxies, those days would be gone. Each civilization would now have to depend only on what they have within their own galaxy. All connections would be lost. The dream of a universe held together by shared science, constant communication, and endless curiosity would one day fade into nothing more than a distant memory. No matter how wise or advanced a species might become, they would never be able to escape the ultimate law of the cosmos, the unbreakable speed limit of light itself. The laws of physics draw a line that no amount of imagination or invention can cross. Even the most incredible machines of the far future, the kind we can barely imagine today, would not be able to leap across the ever-growing space that pushes galaxies farther and farther apart. And yet, not all hope would be gone. Within each galaxy, or inside small families of galaxies still bound tightly by the pull of gravity, life and intelligence could still carry on. Civilizations living in those cosmic islands could explore their surroundings, build connections, and even flourish. On these smaller scales, gravity is stronger than the tearing effect of cosmic expansion. It keeps the stars, the planets, and the galaxies themselves held together against the wider stretching of the universe. In these safe havens, activity, creativity, and discovery could still continue for ages beyond measure. But this raises a haunting question. If civilizations do survive in that distant and lonely future, how will they face the silence of isolation? Will they try to leave behind signs of their existence? Vast records carved into matter, glowing messages written in light, or strange signals cast out into the cosmic sea, hoping that someone, somewhere, might one day discover them? Or realizing the futility of reaching the unreachable, would they instead turn inward, pouring their energy into their own galaxies? Perhaps they would find meaning not in reaching the rest of the universe, but in nurturing what they have, growing wiser, learning deeper truths, and striving to endure in their own corner of the infinite night, even if they never again hear from the rest of the cosmos.